Hello there, and welcome to Science for Sleep, where we let curiosity take the long way around and drift through science at a pace that makes room for rest. Tonight we're going to lift our gaze far above, beyond the clouds, past the familiar stars, and into the question of just how far our galaxy really stretches. It might sound simple at first, like asking where a town begins and ends, or how many streets lie between the centre and the outskirts. But a galaxy isn't a town. It isn't something with a neat city limit sign, or a fence you can point to. It's a collection of hundreds of billions of stars, rivers of gas and dust, clusters of ancient suns, hidden threads of invisible matter, and a halo that doesn't exactly stop. It just thins. Our home galaxy, the Milky Way, is vast beyond ordinary imagination, and even the word vast hardly does it justice. The deeper we look, the more we discover that the edge isn't a wall but more of a blur, a fading into something else, and that raises questions about what it means to belong inside a galaxy, and what it means to drift beyond. Before we step too far, I'd like to ask you something, just as a way of anchoring ourselves. Where are you listening from tonight? Not in the cosmic sense, but in the ordinary one. Are you tucked into bed? Are you sitting in a quiet corner with a cup of tea? Or are you lying back with your eyes half closed, letting the day dissolve? And if you glance at the time, what hour is it where you are? Perhaps early evening, perhaps the middle of the night, perhaps dawn itself just beginning to touch your window. The thought is soothing, isn't it? That across the world, in countless different time zones, people are sharing this same moment with you, each in their own small corner of the Earth, under the same galaxy we're about to talk about. If you find yourself drifting as we go, that's perfectly fine. In fact, that's the whole idea. You're welcome to let this just wash over you like quiet background sound, or to hold on to each detail as long as you'd like. And if you find this space helpful, I'd be grateful if you left a like on the video, maybe even subscribed, because it lets this calm little corner reach others who might need a soft voice and a bit of wonder to carry them towards sleep. So let's begin, not with equations or cold numbers, but with a gentle thought. Imagine standing on a dark night far from city lights. You look up and you see that hazy band arching across the sky, like a mist of faint light. That's our galaxy as seen from the inside. Billions of stars so far away that their glow blends into a single sweep. It looks like a streak, but it's really a disk, and we're inside it. Already that's a strange place to start because most of us are used to thinking about seeing things from the outside. You look at a globe, you see the shape of the Earth. You look at a picture of a building, you see the whole structure. But with the Milky Way, we live within it, and so our perspective is tilted, limited, and a little confusing. It's like trying to figure out the shape of a forest when you're standing in the middle of the trees. Astronomers have spent centuries trying to piece together what the Milky Way looks like and how far it stretches, and the story is one of discovery and revision. For a long time, people thought the entire universe was just the stars we could see in our own galaxy. The word universe and Milky Way were almost interchangeable in older times. Only in the past 100 years did we realize that there are countless other galaxies, each one its own vast island of stars, and that ours is simply one among billions. That changed everything, but it also forced us to ask, if our galaxy is just one island, where do its shores lie? We can start with the bright parts, the parts you might picture when you hear the word galaxy. The spiral disk, stretched with arms of stars that curl around the centre. That disk itself is already enormous, around 100,000 light-years across. A light-year is the distance light travels in a year, nearly 10 trillion kilometres, and our galaxy stretches 100,000 of those units side to side. If you tried to cross it travelling at the speed of light, it would still take you 100,000 years. That's just the main body though, the part that shows up in photographs and artist illustrations. But the truth is, the Milky Way doesn't stop at the edge of its visible disk. It reaches out much farther, into a faint halo of stars, gas and invisible dark matter, and that halo can extend several 100,000 light-years more. The tricky part is that this halo doesn't have a sharp boundary. It's not as though you fly past one star and suddenly you're out. Instead, the density of stars and material just gets thinner and thinner. Like the air as you climb higher in Earth's atmosphere, it never really ends at a sudden ceiling. It just fades until it's indistinguishable from what lies between galaxies. This raises a deep question. When does the Milky Way stop being the Milky Way? Is it when the last star we can recognize as part of it appears? Or is it where its gravitational pull no longer dominates? Or perhaps the edge is defined by where another galaxy's influence begins? That's what we'll keep unravelling step by step as we move farther outward from our familiar place near the centre. And speaking of familiar place, it's worth remembering where we are inside this structure. Our solar system sits about 27,000 light years from the galactic centre, not too close to the crowded heart, not too far into the sparse outer edge. You might say we live in a comfortable suburb of the Milky Way, close enough to see the glowing downtown if we could look through the dust, but far enough away to enjoy a relatively calm neighbourhood. From here, astronomers look inward and outward, trying to measure, map, and understand just how far this home of ours extends. The challenge is enormous, because space is not only vast, but also filled with obstacles to measurement. Dust clouds obscure our view, distances are difficult to measure without reliable markers, and the edges are faint. Over time, though, with clever techniques, we've built up a clearer picture. We now know that the Milky Way is not just the disk we see, but also a bulge at its centre, a thick distribution of stars surrounding it, and then a vast halo that stretches outward like a ghostly sphere. Add in the streams of stars torn from smaller galaxies, the companion dwarf galaxies orbiting us, and the invisible glue of dark matter, and suddenly the question of how far it reaches becomes less about a single number and more about layers of structure, each fading into the next. When we talk about those layers, we'll need to think not just in terms of light years, but in terms of what each part is made of and how it contributes to the whole. The disk contains stars, gas, dust, and the patterns of spiral arms. The bulge contains densely packed stars around a central black hole. The halo holds ancient star clusters and invisible matter we infer from its effects. Each of these adds to the reach of the Milky Way, and each tells us something about why galaxies are not neat little packages but sprawling dynamic systems without strict borders. So tonight we'll let ourselves move through these layers one by one. We'll start with the luminous parts we can see, then drift outward into the fainter regions, eventually arriving at the point where we're not sure whether we're still inside or already outside. It's a journey without a single clear ending, but that's part of what makes it so calming to think about. After all, when you ask how far our galaxy actually reaches, you're really asking how far our home extends, and the answer is both grand and gently uncertain. When we ask ourselves what we call home in the stars, we're not simply asking for a label. We're asking about the frame of reference we live in, the place we can point to and say, yes, this is where I belong. On Earth, home can mean a house, a neighbourhood, a city, or a nation. It's a layered idea that grows or shrinks depending on context. In space, home is harder to define because our planet is part of a solar system, which itself is only one thread in a much larger tapestry. To call the galaxy our home is to step back and look at the larger structure that still has a sense of belonging attached to it. Beyond the galaxy, when you start to think about clusters and superclusters, it becomes harder to feel connected. But the Milky Way, with its stars, dust, gas and gravity binding it together, is still something we can meaningfully say we live inside. The first time most of us realise that the band of light in the night sky is the cross-section of our galaxy. It changes the way we see ourselves. It's not just decoration, it's the ceiling of the very room we live in, a reminder that our solar system is tucked inside a disk of stars so vast that even light, the fastest traveller we know, would need 100,000 years to cross it. When you realise that the Earth isn't on the outside looking in, but inside looking across, the word home takes on a larger dimension. Home is not just the Earth, not just the solar system, but the Milky Way itself. This sense of home grows stronger when you consider that our galaxy is not uniform. It's not a simple pancake of stars. It has a centre, arms, clusters, regions of dust and gas, and each of those shapes the way our neighbourhood looks. Imagine walking through your city or town. Some parts are dense with buildings, others open with parks, others industrial and hard to navigate. The Milky Way has its own layout like that. Where we live, the Sun is part of an arm called the Orion Spur, a small offshoot between two larger arms known as Sagittarius and Perseus. That spur is a relatively quiet suburb, not overcrowded with stars, not empty either. It's the kind of location that might make life possible, because we're not constantly bombarded by radiation from too many nearby stellar neighbours, but we're also not so isolated that we lack the raw materials of star formation. Calling the Orion Spur our neighbourhood is a reminder that home is scale dependent. If you zoom in, home is the solar system. If you zoom out, home is this spur. Zoom farther, and home is the entire spiral disk. Each step outward expands the boundary of what we mean by home, and yet it all remains part of the same galaxy. The reason this matters is that when we ask how far our galaxy reaches, we have to decide at what level we're counting. Do we stop at the bright disk? Do we include the halo? Do we consider the gravitational reach that holds satellites and streams of stars? Each answer shifts the size of our home. It's important to reflect on how fragile this sense of place is. For most of human history, people didn't know they lived in a galaxy at all. They thought the stars overhead were fixed lights in a dome, or perhaps scattered across infinite space without pattern. Only in the early 20th century did astronomers prove that the Milky Way was a galaxy, and that there were other galaxies beyond it. Before that, the term universe meant what we now mean by galaxy. To them, home was the only star system. To us, home is one of billions of galaxies. The shift is dramatic, and it shows how easily our sense of home changes with knowledge. Another layer comes from the way we experience the galaxy from within. The dust and gas between stars creates a kind of veil. If you try to see toward the galactic centre, much of it is obscured. That obscurity means our home is partly hidden from us, as if you were trying to understand your own town while half the streets were covered in fog. Yet, we still manage to reconstruct its shape through radio waves, infrared surveys, and the motions of stars. That process of piecing together the unseen has become part of what it means to call the Milky Way home. It's not just the stars we can see, but also the structures we infer. There's also the matter of belonging in a galaxy filled with so many stars. 100 to 400 billion stars depending on the estimate. Each one with its own potential planets, some perhaps with life. Our Sun is one among them, neither the largest nor the smallest, neither at the centre nor at the edge. When you think of home on Earth, you often think of a specific location, a sense of being rooted. In the galaxy, home is more diffuse. It's not about one address. It's about being part of a system where gravity ties everything together, and where the collective identity is as important as the individual. To call the Milky Way home is to say we belong to a community of stars. The word Milky itself comes from that faint band of light in the night sky, a reminder that ancient observers saw it as a river of milk poured across the heavens. Different cultures had their own interpretations. Some saw it as a path of spirits, some as a scar across the sky, others as a great backbone. Each culture took the same streak of light and gave it meaning, and in that sense, home in the stars is not just scientific but cultural. It's the stories humans have told to explain their place in the galaxy. Science later added numbers and structure, but the feeling of being part of something greater was already there. Another way to think of home is by considering what happens at its boundaries. At the edges of our galaxy, stars become sparse but satellites remain. Small galaxies like the Magellanic Clouds orbit us, bound by the gravity of the Milky Way. They're like outlying towns still under the influence of a larger city. To some astronomers, they're part of our home because they orbit with us. To others, they're neighbours, separate but close. Again, the line is blurry, and it forces us to accept that home is not a fixed boundary, but a gradient. Home also means safety, and in that sense, the galaxy provides a bubble of protection. The magnetic fields of the Milky Way, the distribution of gas and dust, even the halo of dark matter, all shape the environment in which we live. They influence the cosmic rays that reach us, the density of nearby stars, the rate of collisions between systems. Our place within the galaxy isn't random. It's part of a balance that allows life to exist on Earth. The concept of a galactic habitable zone has been proposed, suggesting that only certain regions of a galaxy are stable enough and calm enough for complex life to evolve. Too close to the centre, and radiation is overwhelming. Too far in the outer edges, and heavy elements needed for planets are scarce. We find ourselves in a middle zone, not unlike the Goldilocks zone around a star. That too becomes part of what it means to call the Milky Way our home. What makes this thought especially grounding is that our home in the stars is constantly moving. The Sun orbits the centre of the Milky Way at about 828,000 kilometres per hour. Even at that speed, it takes around 225 million years to make one full circuit. That means in all of human history the solar system hasn't even completed a single lap around the galaxy. Dinosaurs lived in a different sector of the Milky Way than we do now. Every orbit reshuffles our place, so that home is not static. It's more like a journey around a vast track. To call the galaxy our home is to recognise that we're passengers, moving along with billions of others. This constant motion ties back to the larger structures the Milky Way is part of. Our galaxy belongs to a small group called the Local Group, which also includes Andromeda and dozens of smaller galaxies. Beyond that, it's part of the Virgo supercluster. But the further out you go, the less personal it feels. It's difficult to call the Virgo supercluster home in the same way we call the Milky Way home. The connection weakens with distance. The galaxy feels personal because it's the largest structure where our belonging still feels tangible. When you put all this together, the idea of home in the stars becomes more than just a location. It's a sense of identity, a way of situating ourselves in the cosmos. It includes the visible disk, the spiral arms, the halo, the satellites, the streams of stars, the invisible matter, and even the cultural stories we've woven. It's layered, complex, and fuzzy at the edges, but it's still home. And asking how far it reaches is really asking how far this sense of belonging extends. When we picture our galaxy, the first image that usually comes to mind is that of a great spiral, arms sweeping outward, glowing bands of stars and dust curling around a central bulge. That's not because we've ever stepped outside to look at it from above, but because over time, through countless observations and comparisons with other galaxies, we've pieced together its overall form. It might surprise you to know that until the middle of the 20th century, astronomers were still debating its exact structure. Today, we're fairly confident that the Milky Way is a barred spiral galaxy, meaning that at its centre there isn't just a round bulge, but a stretched bar of stars, and from the ends of that bar the spiral arms extend outward. That bar alone is tens of thousands of light-years long, which means that even the feature that seems like a detail in a diagram is itself immense on human scales. The shape matters, because it's what holds us together. Gravity is the obvious glue, but the distribution of stars and gas into this disk and bar is what creates the stable patterns we observe. The spiral arms are not fixed like the blades of a pinwheel. They're regions of higher density, like traffic jams in which stars, gas and dust temporarily pile up before moving on. As matter moves through these arms, the compression can trigger star formation, giving the arms their bright youthful glow. It's this repeating pattern of density waves that maintains the spiral look. Without it, the galaxy might still exist, but it would appear more as a fuzzy disk rather than the structured form we're familiar with. At the heart of the Milky Way lies the central bulge, a roughly spherical distribution of stars, many of them old, surrounding the supermassive black hole known as Sagittarius A. That black hole, with a mass about 4 million times that of the Sun, anchors the very centre. The bulge itself spans thousands of light years and contains a mix of old red stars and some younger populations influenced by the bar. It's denser than the regions we inhabit, meaning stars there are closer together, and the gravitational environment is far more intense. When you think of shape, it's not just geometry, but density, and the bulge demonstrates how the galaxy thickens at the core before flattening into a wide disk. The disk is where most of the familiar features reside. It's thin compared to its diameter, only about 1,000 light-years thick in many places, yet spreading out to about 100,000 light-years across. Within this flattened plane lie the spiral arms, star-forming regions, gas clouds, and the majority of bright stars. Our Sun orbits within this disk, bobbing slightly above and below the central plane over millions of years. This thinness is what gives the Milky Way its striking band when seen from Earth. We're looking edge-on through the disk where the density of stars appears greatest, and that creates the luminous streak across the sky. What's remarkable is that the galaxy doesn't stop at the disk. Beyond it lies the halo, a roughly spherical distribution of stars, star clusters, and dark matter that extends hundreds of thousands of light-years outward. The halo is far less dense, with stars separated by immense distances, but it's part of the galaxy's overall shape. It's easy to forget it when we look at pictures, because photographs emphasize the bright disk and arms, but the halo plays a crucial role in the dynamics of the galaxy. The orbits of globular clusters, some of the oldest stellar systems in existence, trace paths through this halo. These clusters act like markers, telling us the gravitational extent of the Milky Way and revealing that our home is far larger than the bright central disk would suggest. Dark matter adds yet another invisible layer to this shape. Observations of how stars orbit at various distances from the galactic centre show that their speeds don't decrease as expected if only visible matter were present. Instead, they remain higher, indicating that a vast amount of unseen mass surrounds the galaxy. This dark matter halo is thought to extend far beyond the visible stars, giving the Milky Way a shape that cannot be drawn with light alone. While we don't yet know exactly what dark matter is, we can measure its effect, and that effect shapes the galaxy's gravitational pull. Without it, the spiral arms and disk might not hold together in the same way. When we say shape, we're also talking about motion. The entire disk rotates, though not like a solid wheel. Different parts move at different speeds, a pattern known as differential rotation. Near the centre, stars orbit more quickly. Farther out, they move more slowly. But the presence of dark matter changes this expected drop-off, creating what's called a flat rotation curve. This is one of the main pieces of evidence for the unseen halo. The galaxy's shape, then, is not static. It's a dynamic arrangement where billions of stars trace paths that together create the form we recognise. It's worth pausing to think about how unusual this shape is on the scale of the universe. Not all galaxies are spirals. Some are ellipticals, massive but lacking distinct arms, more like football-shaped swarms of stars. Others are irregular, distorted by gravitational interactions. The Milky Way's spiral structure is a product of its history, the accumulation of matter, the influence of nearby galaxies, and the ongoing processes of star formation and gravitational dynamics. Calling it a barred spiral is a way of situating it within a broader family, but each spiral galaxy has its own particular quirks. Ours happens to have a central bar, 4 main arms with smaller spurs, and a halo rich with ancient clusters. From our perspective inside, the shape isn't easy to grasp. We can't simply fly out and take a picture. Instead, astronomers rely on indirect methods, mapping gas clouds with radio waves, tracing the positions of stars with infrared surveys, using parallax to measure distances, and piecing together the distribution from multiple vantage points. Missions like Gaia have given us unprecedented maps, showing the motions of over 1 billion stars, and from these we reconstruct the spiral structure. It's a slow process, like trying to map a city by looking at lights through the fog, but over time the outline becomes clearer. Even so, the Milky Way shape isn't permanent. Over billions of years it will change. Spiral arms may wind tighter or loosen, interactions with dwarf galaxies may stir the disk, and eventually the entire structure will be transformed when we merge with Andromeda in about 4 billion years. That collision will reshape the galaxy into something new, perhaps an elliptical form, erasing the spiral arms we now see. In that sense, the shape that holds us together is temporary, a stage in a long cosmic evolution. Thinking about this shape also brings us back to the idea of boundaries. The disk has a measurable edge, the halo a fainter limit, but there's no single line where the Milky Way stops. The shape is defined not by walls but by gradients of density. This is why astronomers often talk about scale lengths or characteristic radii rather than hard edges. It's an acknowledgement that our home doesn't end abruptly but tapers into intergalactic space. The shape we see is as much about where stars are common as about where they fade into isolation. What ties all of this together is gravity. The bar, the arms, the disk, the bulge, the halo, all are maintained by the mutual pull of billions of stars and dark matter. Without gravity, the structure would disperse. With it, the galaxy maintains its coherent form for billions of years. In that sense, the shape that holds us together is more than geometry. It's the result of countless interactions, every star tugging on every other, every orbit contributing to the balance. From our small location in the Orion Spur, it's difficult to see the whole, but we can feel its influence. The Sun's orbit is guided by the galaxy's mass distribution. The spiral arms influence the rate of star formation in our neighbourhood. The halo and dark matter determine the speed of our rotation. All of these are ways the shape of the Milky Way reaches into our everyday reality, even if we don't notice it. The galaxy's form isn't just an abstract diagram, it's the structure we live inside, the pattern that makes our night sky what it is. When you think of our galaxy, the image that often lingers is the graceful swirl of spiral arms. They are the signature feature of the Milky Way, and they give it the shape we imagine when we hear the word galaxy. From a distance, they look like fixed structures, almost like ribbons of light curling outward. But once you step closer, and once you examine them with care, it becomes clear that the arms are not solid bands. They're more like patterns, regions where stars, gas and dust are temporarily gathered in higher density, passing through as they orbit. In other words, they are waves of concentration, not permanent trails. That distinction is important because it explains both how the galaxy holds its form and why star formation is tied so strongly to these arms. Our own location is not in a major arm, but in a smaller feature known as the Orion Spur. This spur is a kind of side street between two of the larger arms, Sagittarius on one side and Perseus on the other. From where we sit, it's difficult to see the pattern clearly, because we're inside it, looking along the plane of the disk. To map the arms, astronomers use radio telescopes to trace hydrogen gas and molecular clouds, because these reveal the spiral structure more reliably than visible light. Dust blocks much of the visible band, but longer wavelengths pass through, giving us a map that we can compare to the shapes of other galaxies. By doing this, astronomers have concluded that the Milky Way has 4 main arms, with smaller spurs and branches connecting them. The arms are the cradles of stars. As gas clouds move into these higher density regions, they are compressed. That compression triggers the collapse of molecular clouds into new stars. This is why spiral arms glow so brightly. They're filled with young, massive stars that burn hot and blue, lighting up their surroundings. These stars don't live long, only a few million years, so they never wander far from where they were born. Their light outlines the arms, marking them for us to see. Without these massive stars, the arms would be much harder to identify. Inside the arms, the process of star formation continues at many scales. Dense knots within molecular clouds give birth to clusters, while the surrounding gas is sculpted by stellar winds and radiation. This constant cycle means the arms are places of both creation and destruction. Stars form, shine, and explode as supernovas, enriching the interstellar medium with heavier elements. Those elements are then incorporated into the next generation of stars and planets. In a sense, the arms are factories continually renewing the galaxy. Our Sun itself likely formed in one of these arms billions of years ago before settling into its current orbit. The pattern of the arms is maintained by what's known as density wave theory. In this view, the arms are not fixed groups of stars moving together, but rather waves of density that stars and gas move through, much like cars moving through a traffic jam. The traffic jam itself holds its position even though the individual cars pass in and out of it. Similarly, the spiral arms persist as long-term features, even though individual stars only spend part of their orbit within them. This explains how the Milky Way maintains a spiral pattern over billions of years without winding itself too tightly. There are alternative models too, such as the idea that arms may be more transient, forming and dissolving over time due to gravitational interactions and instabilities. Observations of other galaxies show a variety of spiral structures, from well-defined grand design spirals to more flocculent, patchy ones. The Milky Way seems to be somewhere in between, with a central bar driving the structure and a mix of strong arms and smaller spurs. What this tells us is that spiral arms are not static architecture, but living features, shaped by the dynamics of the galaxy. From our vantage point, the spiral arms also define much of what we see in the night sky. Many of the constellations we recognize contain stars that belong to the same arm we're part of. The Orion Nebula, one of the brightest star-forming regions visible from Earth, is part of the Orion Spur. Other bright nebulae and clusters trace the outlines of the arms nearby. When we look toward the center of the galaxy, our view is blocked by dust, but the arms closest to us reveal themselves through these concentrations of young, bright stars. The arms also play a role in shaping the chemical makeup of the galaxy. Because star formation is concentrated there, the arms are enriched more quickly with heavier elements produced in supernovae. That enrichment spreads as stars move out of the arms, but the pattern of higher metallicity near the arms is an important part of how the galaxy evolves. Planets like Earth, rich in heavy elements, are the result of this cycle. Without the arms concentrating star formation, the distribution of elements might look very different, and planets capable of supporting life might be far less common. The arms aren't only about stars and gas, they're also sculpted by interactions with smaller galaxies. Over time, the Milky Way has absorbed many dwarf galaxies, and these interactions can stir the disk, enhancing spiral patterns or even creating new ones. Streams of stars left behind by these mergers weave through the disk, adding to the complexity of the arms. The Sagittarius dwarf galaxy, currently being torn apart by the Milky Way's gravity, is one example. Its debris has influenced the structure of the outer disk and may have helped shape the arms we see today. There's a human side to this too. The arms are where astronomers often direct their searches for new exoplanets, because young stars and clusters are more likely to be found there. Many of the exoplanets discovered by missions like Kepler are located within or near the spiral arms. When we think about the possibility of life elsewhere in the galaxy, we're really thinking about life that might exist in these same swirling regions. The arms become not just a structure, but a context for imagination, a stage on which other civilizations might exist. It's also important to note that not all arms are equally prominent. The Sagittarius and Perseus arms are considered major arms, while the Orion Spur is a smaller structure. Yet from our perspective, this spur is our immediate environment. That perspective matters. To someone living on a planet in the Perseus arm, our spur might seem insignificant. To us, it's the whole neighbourhood. This relativity of scale is part of what makes the arm so fascinating. They're both immense structures and personal landmarks depending on where you stand. Studying the arms is challenging because of our position. We can't see the entire spiral from above, so we have to rely on indirect mapping. One method involves measuring the distribution of giant molecular clouds, the raw material of stars. Another is to use parallax to determine the distances to young, bright stars, then trace their positions. Over decades, these methods have built a map that, while still incomplete, gives us a good sense of the overall structure. The Gaia mission has added extraordinary detail by charting the motions of over 1 billion stars, allowing astronomers to see patterns that confirm and refine the models of the spiral arms. What emerges from all this effort is a picture of a galaxy with a complex but coherent spiral structure, driven by density waves, star formation, and interactions with its surroundings. The arms are not static, not permanent, but they are long-lived enough to define the Milky Way's shape. They are both a dynamic process and a visual feature, the most recognizable aspect of our galactic home. When you look up at the night sky, even from a very dark place, you might be able to count a few thousand stars with the naked eye. That sounds like a lot, but compared to the number of stars in our galaxy, it's a vanishingly small fraction. Astronomers estimate that the Milky Way contains somewhere between 100 billion and 400 billion stars. The range is wide because counting stars isn't like counting coins in a jar. The stars vary in brightness, in distance, and in how easily they can be hidden by dust and gas. Some are faint red dwarfs, barely glowing compared to our Sun, and others are massive blue giants that burn so brightly they can be seen across great distances. To count them, astronomers have to rely on indirect methods, extrapolating from surveys of smaller regions and building models of the galaxy as a whole. The difficulty begins with the simple fact that we're inside the system we're trying to measure. It's like trying to count all the trees in a forest while standing among them. Your view is limited by what's in front of you. Dust obscures your sight lines. Some trees are too far away to see clearly. To overcome this, astronomers divide the galaxy into different populations of stars, estimate the density of each population, and then extend those estimates across the entire structure. Even then, uncertainties remain. For example, red dwarfs make up the majority of stars, but they're faint, so they're easy to miss at great distances. If you underestimate their number, your total count will be too low. Another layer of difficulty comes from binary and multiple star systems. Many stars exist in pairs or groups, orbiting each other. From a distance, these can appear as single points of light. If you assume every point is a single star, you'll undercount. Careful observation reveals that binaries are common, perhaps more common than solitary stars like our Sun. So when astronomers build models, they have to account for this. Each visible light source might represent more than one star. Despite these challenges, surveys like those conducted by the Gaia spacecraft have given us an extraordinary database of stellar positions and motions. Gaia has mapped over 1 billion stars, still only a fraction of the galaxy, but a fraction large enough to allow reliable extrapolation. By understanding the distribution of stars in the disk, the bulge, and the halo, astronomers can make more precise estimates of the total number. These models suggest that the Milky Way's population falls somewhere in that vast range of 100 to 400 billion. Even at the low end, the number is staggering. To put this into perspective, if you tried to count the stars one by one, saying one number every second without stopping day and night, it would take you thousands of years to finish. And that's assuming the lower estimate. At the higher estimate, it would take several millennia more. The human mind isn't well equipped to grasp numbers on that scale. What we can do is create analogies. For instance, there are about 7.8 billion people on Earth. If each person were given their own personal set of stars, you could assign each person more than a dozen stars and still have billions left over. The galaxy is not just abundant, it's overwhelming. The stars aren't evenly distributed either. Most of them lie in the thin disk where the spiral arms are. That's where star formation is most active, and it's where the majority of stellar mass is concentrated. The bulge at the centre contains many older stars, packed more densely than in the disk. The halo, on the other hand, has fewer stars, but they're often in clusters that trace back to the earliest history of the galaxy. Counting them all requires careful accounting across these regions. You can't just average density across the disk and multiply by volume. You need to respect the differences in stellar populations. Among the billions, the majority are small red dwarfs. These stars are cooler and dimmer than the Sun, but they live far longer. Some will burn steadily for trillions of years, long after more massive stars have burned out. Because they're so faint, they can be difficult to detect beyond a few dozen light years, but surveys of nearby regions suggest they make up about 3/4 of all stars. In other words, most of the stars in our galaxy are invisible to the naked eye, hidden not by dust but by faintness. The stars we see at night are the exceptions, the brighter and rarer ones. On the other end of the spectrum are the giants. Massive stars burn hot and bright but live short lives. They're far less common, but their brilliance makes them easy to spot. They shape their surroundings with radiation and stellar winds, carving bubbles in the interstellar medium. They end their lives in supernovae, creating heavy elements and leaving behind neutron stars or black holes. Even though they're rare, their impact on the galaxy is outsized. Counting stars isn't just about tallying numbers, it's about recognizing the roles each type plays in the galaxy's ecosystem. Clusters add another dimension to the problem. Open clusters are groups of young stars born together from the same cloud. They gradually disperse over time, but while they last, they're rich with stars in close proximity. Globular clusters, on the other hand, are ancient, tightly bound groups of hundreds of thousands of stars. These clusters orbit in the halo and serve as markers of the galaxy's outer reaches. Including them in the total count adds not just numbers but also context, because they reveal the history of star formation, stretching back over 10 billion years. There's also the matter of stellar remnants. White dwarfs, neutron stars and black holes are no longer shining in the way we normally think of stars, but they're still part of the galaxy's population. White dwarfs, the remnants of stars like our Sun, are especially numerous. They may account for a significant portion of the stellar mass. Detecting them requires specialized surveys because they're faint and small. But leaving them out would underestimate the true stellar population. When astronomers say there are hundreds of billions of stars, they're including all of these: the blazing giants, the dim dwarfs, the clusters, and the remnants. The number itself is almost beyond comprehension, but what makes it meaningful is how it reflects the complexity of the galaxy. Each star is its own system, many with planets, some perhaps with life. Counting stars is not just an exercise in statistics, it's an attempt to measure the richness of our home. The sheer scale of this richness also affects how we think about edges. If stars thinned out quickly beyond a certain radius, the galaxy would feel more bounded. But because even faint stars and clusters extend far into the halo, the count doesn't drop to zero at a neat boundary. Instead, it fades. The further out you go, the sparser the stars become, but there are still stars, still clusters, still traces of structure. That's why counting stars isn't only about knowing how many, it's about understanding how far they extend and how their distribution shapes our definition of the galaxy's reach. The effort to count also connects to larger cosmic questions. If our galaxy has hundreds of billions of stars and each has planets, how many Earth-like planets might exist? How many chances for life? Surveys like Kepler have suggested that planets are common, perhaps more common than stars themselves, since many stars host multiple planets. Extrapolating from nearby stars, some estimates suggest there could be tens of billions of potentially habitable planets in the Milky Way alone. That makes the number of stars more than just an abstract figure. It's a measure of potential homes, of possible futures, of places where someone else might be asking the same questions. Counting stars also teaches us about history. The age distribution of stars reveals when bursts of star formation occurred. Younger stars cluster in the spiral arms, while older stars dominate the bulge and halo. By tallying and categorizing them, astronomers reconstruct the galaxy's past. The population of metal-poor stars in the halo, for instance, shows us remnants of the earliest generations formed when the universe had not yet produced many heavy elements. These stars are fossils, telling us about conditions billions of years ago. Counting them is like counting tree rings to learn the age and growth of a forest. And yet, for all our progress, the exact number remains uncertain. That uncertainty is a reminder of both the limits of observation and the immensity of the galaxy. We don't need an exact figure to appreciate the scale. Whether it's 100 billion or 400 billion, the difference is small compared to the overwhelming reality of the number itself. What matters is that the galaxy is populated far beyond what we can see with our eyes, and that the attempt to count is as much about perspective as precision. So when we talk about counting stars in a sea without shores, we're acknowledging both the abundance and the elusiveness of the task. It's a sea because the stars stretch in every direction, beyond the horizon of our senses. It's without shores because the edges are not sharp but fade gradually into the emptiness between galaxies. To count is to try to impose order, but the truth is that the vastness resists neat totals. Still, by counting, by estimating, by surveying, we build a clearer picture of our place, and that picture is one of extraordinary richness. When you step outside on a clear night and look up, the sky feels wide open. The stars shine without resistance, and it's easy to imagine that the entire galaxy lies revealed before you. But what you're actually seeing is only a fraction of what's there. Between us and much of the Milky Way stretches an enormous veil of dust, fine particles scattered through interstellar space. This dust is not like the dust on your bookshelf. These grains are tiny, made of carbon, silicates and ices, but spread over immense distances. Together they form clouds and filaments that absorb and scatter starlight. The result is that much of the galaxy's structure is hidden from direct view. The bright band of the Milky Way across the sky is striking, but in truth it's just a glimpse through small gaps in that veil. The dust doesn't just block light, it reddens it. Shorter wavelengths like blue light are scattered more effectively, while longer wavelengths like red pass through more easily. This process, called interstellar reddening, is why stars seen through heavy dust appear redder than they truly are. For astronomers, this effect complicates the task of measuring distances and understanding stellar populations. You have to correct for the dust, but to correct, you first need to know how much is there, and that varies across the sky. Some regions are relatively clear, while others are thick with obscuring clouds. The regions near the galactic centre are among the most heavily obscured. Dust there is so dense that visible light can't penetrate. For centuries, the centre of the Milky Way was invisible to us. Only with the advent of infrared and radio astronomy could we finally peer through the dust and discover the crowded heart of the galaxy, with its dense bulge of stars and its central black hole. In a way, dust shapes our perception of what the galaxy looks like. If we could see it without obstruction, the Milky Way would appear very different, perhaps more like the photographs we take of external spiral galaxies. Instead, we experience it as a streak punctuated by dark rifts, the most famous being the Great Rift in the summer sky, a series of obscuring dust lanes that cut across the Milky Way's band. These dust lanes aren't empty, they are the raw material for future stars and planets. Within them, dense pockets collapse under gravity, forming new stellar nurseries. The Orion Nebula, for example, is a nearby region where this process is actively happening. What looks like a cloud blocking our view is actually a site of creation. This dual role makes dust both an obstacle and a source of fascination. It hides, but it also gives birth. The next generation of stars will emerge from these same dusty regions that frustrate our attempts to see clearly. On larger scales, dust is part of the interstellar medium, the mix of gas and particles that fills the disk of the galaxy. The distribution of this medium is uneven, with clumps, filaments and bubbles carved out by stellar winds and supernovae. This unevenness means that our view changes depending on where we look. Towards some directions, we can see thousands of light years with little obstruction. Toward others, We can barely see past the nearest arm. This patchwork complicates the task of mapping the galaxy's size and structure. It's like trying to sketch a landscape with fog rolling in and out at random. To work around this, astronomers use wavelengths of light that can penetrate dust. Radio waves, for instance, pass through easily. By mapping the distribution of neutral hydrogen, which emits a characteristic 21 centimeter line in radio frequencies, astronomers can trace the spiral arms even where dust blocks visible light. Infrared light also penetrates dust better than visible light. Surveys in the infrared have revealed countless stars near the galactic centre that were invisible before. X-rays and gamma rays, at the opposite end of the spectrum, also bypass dust, though they show us more energetic processes rather than ordinary stars. By combining all these wavelengths, we can build a fuller picture of the galaxy, one that corrects for the veil in front of us. Still, even with these tools, the dust leaves its mark. It creates uncertainty in distance measurements. If a star appears dimmer than expected, is it because it's farther away, or because dust has absorbed some of its light? Parallax measurements, like those provided by Gaia, help resolve this. But even then, corrections for reddening must be applied. This is why maps of the Milky Way remain works in progress. Each new survey refines our understanding, lifting the veil a little more but never completely. The scale of the dust is staggering. Estimates suggest that about 1% of the interstellar medium's mass is in the form of dust, with the rest being gas. That might sound small, but given the galaxy's size, it adds up to millions of solar masses worth of dust. Spread across the disk, it forms a thin layer, mostly confined to the galactic plane. This explains why the band of the Milky Way is both bright and interrupted. We're looking along the plane, where stars are concentrated, but also where dust is thickest. Above and below the plane, the view clears, and we can see more distant galaxies beyond. For us, this veil is both a frustration and a gift. Without it, the sky would be brighter, but perhaps less dramatic. The dark lanes cutting across the Milky Way give it texture and mystery. They remind us that our view is partial, that there are hidden depths. In scientific terms, they force us to innovate, to look in new ways, to develop instruments that can see what our eyes cannot. The history of astronomy is full of breakthroughs driven by the need to pierce this dust. Infrared detectors, radio arrays, space-based observatories, all were developed in part to get past the obstruction. In that sense, the veil has guided our progress, shaping not just what we see but how we learn. The veil also has implications for life. Dust grains are the seeds of planets. In protoplanetary disks around young stars, dust grains collide, stick together, and gradually grow into pebbles, rocks, and eventually planets. Without dust, there would be no Earth, no oceans, no soil. The same particles that block our view are the building blocks of our existence. When astronomers talk about cosmic dust, they're not talking about something trivial. They're talking about the foundation of worlds. Understanding dust also helps us place boundaries on the galaxy. Because dust is concentrated in the disk, it marks the regions where star formation is active. The halo, by contrast, is largely dust-free. By mapping where dust thins out, we can identify where the disk ends and the halo begins. This transition isn't sharp, but it's another way of tracing the galaxy's reach. The veil that hides our view also outlines the shape of our home. When you consider how much of the galaxy is hidden by dust, it's humbling. The beautiful pictures of spiral galaxies we see in astronomy books are what the Milky Way would look like if we could step outside and look down on it. From inside, though, we see only through small windows, peering between the clouds. Our understanding comes not from direct sight, but from assembling fragments. The dusty veil reminds us that our perspective is limited, and that knowledge requires patience. Measuring distance on Earth is simple. You can take a tape measure, a ruler, or a GPS signal, and you'll know how far one place is from another. But in the galaxy, there are no tape measures stretching between stars. Light travels immense spans, and the space between objects is empty. To know how far our galaxy reaches, we first have to understand how to measure the distances to the things inside it. Without that knowledge, we can't build maps, we can't count stars reliably, and we can't describe the structure with confidence. Distance is the foundation of scale, and in cosmic darkness that foundation isn't easy to establish. The most direct method astronomers have is parallax. As the Earth orbits the Sun, our viewpoint shifts. Against the more distant background, nearby stars appear to move slightly back and forth. The angle of this apparent shift can be measured, and from it the distance can be calculated using geometry. This is the same principle you use with your eyes to judge depth. Each eye sees from a slightly different perspective, and your brain calculates distance from the difference. With stars, the baseline is not the separation of our eyes, but the diameter of Earth's orbit, about 300 million kilometers. Even with such a large baseline, the shifts are tiny, fractions of an arc-second. That's like measuring the width of a coin from thousands of kilometers away. Still, with modern instruments, we can detect these shifts with extraordinary precision. Parallax works best for stars within a few thousand light-years. Beyond that, the shifts are too small to measure reliably. For centuries, this limited our ability to chart the galaxy. But with space telescopes like Hipparcos and Gaia, parallax has been extended much farther. Gaia, in particular, has mapped distances and motions for over 1 billion stars, creating the most detailed three-dimensional map of the Milky Way ever made. This has revolutionized our understanding, allowing us to trace spiral arms, measure the thickness of the disk, and estimate the extent of the halo. But parallax isn't enough for the farthest reaches. To probe deeper, astronomers rely on standard candles, objects whose intrinsic brightness is known. By comparing how bright they appear to us with how bright we know they truly are, we can calculate their distance. One important standard candle is the Cepheid variable star. These stars pulsate, growing brighter and dimmer in a regular cycle. The period of their pulsation is directly related to their luminosity. If you measure the period, you know the true brightness. Compare that to the apparent brightness, and you can calculate the distance. Cepheids are bright enough to be seen across much of the galaxy, and even in nearby galaxies, making them essential markers. Another valuable standard candle is the RR Lyrae star, a type of pulsating variable common in globular clusters. These stars are older and less luminous than Cepheids, but they're reliable indicators, especially in the halo. By using them, astronomers can measure the distances to clusters and map the outer boundaries of the Milky Way. Globular clusters orbit far from the galactic centre, some more than 100,000 light-years away, so they provide anchors for estimating the galaxy's extent. Beyond variable stars, astronomers also use the tip of the red giant branch, a well-defined stage in stellar evolution, as a distance indicator. When a star of certain mass reaches this stage, its brightness is fairly consistent, making it another useful standard candle. White dwarf stars, particularly in clusters, can also be used. Each of these methods has uncertainties, but by combining them, astronomers create a ladder of distance measurements, each rung extending farther outward. Even supernovae play a role. Type Ia supernovae, which occur when a white dwarf in a binary system accumulates enough mass to trigger runaway fusion, have nearly uniform peak brightness. While these are more useful for extragalactic distances, they still contribute to our understanding of scales within and beyond the Milky Way. The challenge of distance isn't just academic, it affects everything we think we know about the galaxy. If you underestimate distances, the galaxy looks smaller, denser, and younger. If you overestimate, it looks larger, more diffuse and older. Entire models of galactic structure hinge on getting distances right. For example, the debate about the number of spiral arms in the Milky Way has been influenced by how accurately we can place star-forming regions. Without precise distances, it's easy to misinterpret the arrangement. Dust complicates things further. As we saw earlier, dust absorbs and reddens light, making stars appear dimmer than they really are. If you don't correct for this, you might think a star is farther away than it is. Astronomers work around this by observing in infrared and radio wavelengths, which are less affected by dust, but corrections are still needed. The veil that hides our view also distorts our measurement of distances. Proper motion adds another layer. Stars move across the sky over time, and by tracking these motions in addition to parallax, astronomers can refine distance estimates. Combined with radial velocity measurements, how fast a star is moving toward or away from us, this creates a full picture of stellar orbits. From these orbits, the mass distribution of the galaxy can be inferred, which in turn helps estimate the size and reach of the Milky Way. There are also statistical methods. By measuring the overall brightness of a cluster and comparing it to models of stellar populations, astronomers can estimate its distance. These methods are less precise for individual objects, but they help build the larger framework. They're especially useful when dealing with distant or obscured regions where individual stars can't be resolved clearly. The distance problem is so fundamental that it has shaped entire eras of astronomy. Before accurate distances were available, astronomers debated whether the Milky Way was the entire universe. The discovery that some faint nebulae were actually other galaxies depended on distance measurements. Once we knew that the Andromeda galaxy lay millions of light-years away, it became clear that the Milky Way was not everything. Within our own galaxy, refining distances has similarly transformed our understanding of its size and shape. What's striking is how distance connects to the question of edges. To know how far the galaxy reaches, you need to know how far its stars and clusters extend. If your distance estimates are too short, you'll draw the boundary too close. If they're too long, you might mistake background galaxies for distant Milky Way members. The precision of distance measurements determines the clarity of the edge. Consider the halo again. Globular clusters orbit far outside the visible disk. Measuring their distances accurately reveals that the halo extends hundreds of thousands of light-years. Without these measurements, we might think the Milky Way ended at the disk. The clusters show that our home stretches far beyond what we can see directly. Similarly, stellar streams, remnants of smaller galaxies torn apart by the Milky Way's gravity, trace paths that reach even farther. To follow these streams, accurate distances are essential. In a way, measuring distance in the galaxy is like trying to measure your way through fog with only a lantern. Each method extends your reach a little farther, but never infinitely. By combining lanterns, parallax, standard candles, statistical models, you illuminate more of the fog. Slowly, the outline of the forest emerges. It's not perfect, but it's enough to navigate. At the very centre of our galaxy lies a region unlike the quieter outskirts where we orbit. It's a crowded, dense place filled with old stars, overlapping orbits, heavy dust, and an energy that shapes much of the Milky Way's character. Astronomers call it the bulge, a thickened, roughly spherical collection of stars swelling around the core. While the spiral arms and the disk stretch outward in a thin plane, the bulge rises above and below, forming a central concentration that gives the galaxy its structure. The bulge is ancient. Many of the stars there are more than 10 billion years old, meaning they formed when the galaxy itself was young. Their age makes them redder and cooler than the younger stars found in the spiral arms. But the bulge isn't just a uniform crowd of old suns. There are also younger stars mixed in, likely formed when gas funneled into the centre along the bar and triggered new star formation. This mix of old and young creates a complex population that continues to puzzle astronomers. The bulge is not a simple relic. It's a living region where history and ongoing processes overlap. At its heart lies Sagittarius A, the supermassive black hole with a mass about 4 million times that of the Sun. We can't see it directly, but we can watch the stars that orbit it. Over years of observation, astronomers have tracked stars whipping around an invisible point, moving at tremendous speeds, their orbits curving under the pull of a compact, massive object. These motions are the strongest evidence for the black hole. It anchors the centre, a gravitational engine shaping the dynamics of the bulge. The environment near Sagittarius A is extreme. Stars crowd together more densely than in our neighbourhood, sometimes separated by only a fraction of a light year. Gas clouds swirl inward, heated to millions of degrees as they approach the black hole. Magnetic fields twist and tangle. Occasionally, material falling into the black hole produces flares of radiation, brief bursts that remind us the core is not silent. This activity doesn't dominate the entire bulge, but it gives the central few light years a unique character, a restless energy distinct from the calmer regions farther out. The shape of the bulge itself is not perfectly round. Observations suggest it has a boxy or peanut-like shape, likely the result of the central bar's dynamics. As stars in the bar orbit, they can puff up vertically, creating this thickened structure. From our position inside the disk, we can't see this shape directly, but surveys in infrared have revealed it by mapping the distribution of stars. The result is a bulge that isn't just a sphere of stars, but a structured, elongated form tied to the galaxy's rotation. Studying the bulge is difficult because of the dust along our line of sight. Visible light from the core is heavily obscured. That's why astronomers rely on infrared and radio observations to peer into the centre. Instruments like the Very Large Telescope and the Keck Observatory have tracked stellar motions near Sagittarius A in infrared, while radio arrays have imaged the region with extraordinary resolution. The Event Horizon Telescope even produced the first direct image of the black hole's shadow, confirming what years of orbital studies had shown. These observations open a window into a place once hidden behind the veil. The bulge isn't just an astronomical curiosity. It plays a role in the overall stability of the galaxy. Its mass contributes to the gravitational potential that shapes stellar orbits throughout the disk. Without the bulge, the inner regions of the Milky Way would behave differently. The bar, the spiral arms, and the rotation curve all interact with this central mass. In that sense, the bulge is like the anchor point of the galaxy's form, balancing the forces that hold it together. It's also a record of history. The stars in the bulge carry chemical signatures that reveal how the galaxy evolved. Many are metal poor, meaning they formed before successive generations of stars enriched the interstellar medium with heavy elements. Others are more metal-rich, evidence of later waves of star formation. By studying these populations, astronomers reconstruct the sequence of events that built the bulge. Was it formed quickly, in the galaxy's earliest days, or gradually, through the inflow of gas and mergers with smaller galaxies? The evidence suggests a mix of both processes. The bulge is a fossil record, layered and complex. For us, the bulge is far away, about 70,000 light-years from Earth. Yet it dominates the night sky when we look toward the constellation Sagittarius. That rich region, crowded with stars and nebulae, is our line of sight into the galactic centre. What appears as a hazy glow to the naked eye is, in reality, the combined light of billions of stars packed into the bulge. Long exposures with telescopes reveal a density almost unimaginable compared to our local region. To stand inside the bulge, if it were possible, would be to see a night sky ablaze with stars, far brighter than anything we experience here. The bulge also connects to the larger structures around it. The bar extends through it, funneling gas inward and sustaining cycles of star formation. The disk spreads outward from its edges, while the halo surrounds it on all sides. In this way, the bulge isn't isolated. It's the central knot tying the galaxy together, from which other components flow. Its relationship with the black hole, the bar, and the disk creates feedback loops that influence the galaxy's evolution. Even though it seems remote, the bulge's influence reaches us. The gravity of the central mass shapes the orbit of the Sun and every other star in the disk. The stability of the spiral arms, the thickness of the disk, even the overall rotation of the galaxy are tied to the bulge's presence. It's easy to think of it as a distant curiosity, but in reality it's a central part of the system we inhabit. Looking at the bulge also raises questions about edges again. Where does the bulge end and the disk begin? The transition is gradual, not sharp. Stellar density decreases outward, blending into the thinner disk. Chemically and dynamically, the populations overlap. This lack of a clear boundary mirrors the broader theme of the galaxy: no edges, only gradients. The bulge exemplifies this, fading smoothly into the structures around it. For astronomers, the bulge is also a reminder of the limitations of observation. Even with advanced instruments, dust and distance make it challenging to study. Each new survey adds detail, but also reveals complexity. The more we look, the less simple the picture becomes. The bulge refuses to be reduced to a neat description. It is both ancient and active, structured and diffuse, an archive and a living system. When most people imagine a galaxy, they think of the glowing disk, the spiral arm sweeping outward, the bright bulge at the centre. That's the picture we see in photographs of distant spirals. But the Milky Way, like those galaxies, is more than what shines in visible light. Surrounding the disk is a vast, faint structure known as the halo. It stretches far beyond the bright stars and arms, enveloping the galaxy in a sphere that's difficult to see but impossible to ignore. To ask how far our galaxy reaches is, in many ways, to ask about this halo, because it extends much farther than the luminous parts that first come to mind. The stellar halo is made of ancient stars and globular clusters, relics from the earliest days of the Milky Way. These stars are sparse, scattered across immense volumes, often on elongated orbits that carry them far from the centre. Unlike the orderly rotation of stars in the disk, halo stars move in more random directions, tracing paths that reflect a history of accretion and merger. Many of them likely originated in smaller galaxies that were pulled into the Milky Way and torn apart by its gravity. Their presence is a fossil record of these interactions, a reminder that the halo is not just a sphere of stars but a memory of galactic evolution written across space. Globular clusters are among the most striking features of the halo. Each one contains hundreds of thousands of stars bound tightly together, some of the oldest stars known. They orbit far above and below the galactic plane, their paths taking them tens of thousands of light-years from the centre. From Earth, we can see them as compact, glittering balls through telescopes. They're like lanterns marking the outer boundaries of the galaxy. Some clusters orbit at distances greater than 100,000 light-years, demonstrating that the Milky Way's influence extends at least that far, and likely much farther when dark matter is considered. Dark matter itself forms a halo even larger than the stellar one. We can't see it directly, but we infer its presence from the motions of stars and gas. If only visible matter were present, the outer regions of the galaxy would rotate more slowly than they do. Instead, stars far from the centre orbit at speeds that imply the presence of enormous amounts of unseen mass. This dark matter halo is thought to extend several 100,000 light-years, possibly up to 1,000,000. It gives the galaxy most of its mass, dwarfing the contribution of stars and gas. Without it, the Milky Way wouldn't hold together in the form we see. The halo is diffuse, which makes it difficult to define its edge. Unlike the disk, which has a clear drop in density, the halo just thins out gradually. There's no wall where it ends, only a fading into intergalactic space. Astronomers sometimes define the edge in terms of the galaxy's virial radius, the region within which the galaxy's gravity dominates over the expansion of the universe. For the Milky Way, this radius is estimated to be around 250,000 to 300,000 light-years, though some models suggest even larger values. This means the halo extends far beyond the visible stars, into a realm where the galaxy's influence is real but subtle. Within the halo, streams of stars trace the remnants of past mergers. When a smaller galaxy is pulled into the Milky Way, tidal forces tear it apart, scattering its stars along elongated paths. These streams wrap around the galaxy, faint ribbons barely detectable against the background. They reveal the process by which the halo was built, piece by piece, through the accretion of smaller systems. The Sagittarius stream is a prominent example, the debris of the Sagittarius dwarf galaxy being digested by the Milky Way. Such streams show that the halo is not static. It's a dynamic, evolving structure still being shaped by ongoing interactions. The stellar populations in the halo differ from those in the disk. They're generally metal poor, meaning they lack the heavier elements produced by generations of supernovae. This suggests that many halo stars formed early, before the galaxy was enriched by successive cycles of star formation. Some may even predate the Milky Way itself, born in dwarf galaxies that were later absorbed. Studying these stars provides insight into the early universe, giving astronomers clues about conditions billions of years ago. The halo, in this sense, is not just a boundary but a time capsule. For us, living in the disk, the halo is easy to forget. It's invisible to the naked eye, its stars too faint and spread out to make much impression on the night sky. Yet it surrounds us completely, extending in all directions. To grasp its presence, you have to think not of bright features but of vast emptiness dotted with rare, ancient stars. It's the part of the galaxy that feels least like a home and most like a wilderness, and yet it's still part of the same system. Its faint stars still orbit the galactic centre, bound by the same gravity that holds us. The existence of the halo challenges our sense of edges. If you ask someone where the Milky Way ends, they might point to the edge of the disk. But the halo shows that the galaxy stretches much farther. Even beyond the visible, its influence extends. This complicates the question of how far the galaxy reaches. If you include the dark matter halo, the answer is far greater than if you only consider the stars in the disk. It depends on whether you define the edge by light, by stars, or by gravity. Each definition yields a different boundary, and none is definitive. Observations of other galaxies help put this in perspective. When we look at Andromeda, for instance, we see a bright disk surrounded by a faint halo of stars and gas. Andromeda's halo also extends hundreds of thousands of light years, overlapping with our own Milky Way's halo. In fact, the two halos may already be interacting, blurring the distinction between the galaxies long before their disks merge in the distant future. This overlap reinforces the idea that halos are not just appendages but essential parts of galaxies, shaping their interactions and evolution. The halo also has practical significance for cosmology. By studying its stars and clusters, astronomers can refine estimates of the Milky Way's total mass. This is crucial for understanding our galaxy's place in the local group and its eventual merger with Andromeda. The motions of halo stars provide constraints on how much dark matter surrounds us, which in turn informs models of structure formation in the universe. The halo isn't just a curiosity, it's central to understanding how galaxies form and evolve on cosmic scales. Despite its importance, the halo remains mysterious. We don't yet know the exact shape of the dark matter distribution. Is it spherical, elongated, clumpy? We don't know all the details of its stellar streams, or how many past mergers contributed to its build-up. Each new survey reveals more complexity, suggesting that the halo is less a smooth sphere and more a tangled web of debris. It's the most difficult part of the galaxy to study, but also the part that tells the most about its past. For those of us lying under the night sky, the halo is invisible, but its effects are everywhere. The sun's orbit, the rotation of the disk, the survival of the spiral arms, all are made possible by the mass of the halo. Without it, the Milky Way would not look the way it does. We might never notice it with our eyes, but we live within its embrace. When astronomers first began mapping the motions of stars and gas in galaxies, they expected to see a certain pattern. The further out you go from the centre, the slower stars should orbit, because less mass should be inside their paths. That's what happens in the solar system. Planets closer to the Sun move quickly, while those farther out move more slowly, because the Sun's gravity weakens with distance. But when measurements were made of galaxies, including our own, the stars didn't slow down as expected. Even far from the centre, their speeds remained high. The only explanation was that something unseen was providing extra gravity. That unseen something is what we call dark matter. Dark matter doesn't emit light. It doesn't reflect, scatter, or absorb radiation in any way we can detect directly. yet its gravitational influence is undeniable. In the Milky Way, the rotation curve, the plot of orbital speeds versus distance from the centre, stays flat far beyond the visible disk. This means there must be far more mass than the stars and gas we can see. The conclusion is that the galaxy is surrounded by a vast halo of dark matter, perhaps 10 times more massive than all the visible matter combined. To picture this, imagine the Milky Way as a disk of glowing stars and gas, but around it, extending much farther, is an invisible sphere of mass. That sphere shapes the orbits of stars in the disk, holds the halo of globular clusters in place, and even influences the paths of nearby dwarf galaxies. Without it, the galaxy would fly apart. The ghostly glow isn't a glow of light, but of effect, a presence made visible through motion. The nature of dark matter remains one of the deepest mysteries in science. We know it's not made of ordinary atoms. If it were, we would see its effects in the form of radiation, absorption lines, or other signatures. Instead, it seems to be composed of particles that interact very weakly with normal matter, if at all. Candidates include things like WIMPs, weakly interacting massive particles, or axions, hypothetical particles proposed to solve other problems in physics. So far, none have been detected directly. Despite decades of experiments, dark matter continues to elude us. We only know it's there because of its gravitational pull. The Milky Way offers one of the best laboratories for studying dark matter. By tracking the motions of stars at different distances, astronomers can estimate the shape and size of the dark matter halo. These studies suggest that the halo may extend hundreds of thousands of light years, enveloping the galaxy and blending into the halos of neighbouring galaxies like Andromeda. The overlap hints at how galaxies are not isolated but part of a larger cosmic web, connected through their dark matter envelopes. Streams of stars in the halo also provide clues. When smaller galaxies are torn apart by the Milky Way's gravity, their stars stretch into long trails. The exact paths of these streams depend on the distribution of dark matter. By mapping them, astronomers can infer whether the halo is smooth or clumpy, spherical or elongated. Each stream is like a tracer particle in a fluid, revealing the invisible currents of gravity around us. Even though we can't see dark matter, simulations show what it might look like. Computer models of cosmic structure, seeded with dark matter, produce filaments and clusters that resemble the observed universe. The galaxies form along these filaments, like beads on threads, while vast voids open in between. In this picture, dark matter isn't just an add-on. It's the scaffolding of the cosmos. Without it, galaxies might not have formed at all. The Milky Way itself is the result of dark matter clumping together, pulling in gas and allowing stars to ignite. The invisible halo is not just a current feature, it's the reason we exist. For us, living inside this halo, dark matter is completely intangible. You can't touch it, see it, or feel it in any direct sense. Yet every motion of the sun around the galaxy is governed by it. Our orbit speed, the stability of the disk, the persistence of the spiral arms, all rely on the unseen mass. When you look at the stars in the night sky, you're also looking at a display made possible by dark matter, even though it doesn't shine. The phrase ghostly glow is fitting because dark matter reveals itself indirectly, like a ghost seen only through the movement of objects it disturbs. The glow is not luminous but gravitational, and just as with a ghost story, the more we investigate, the more elusive the source seems. Each experiment designed to detect dark matter directly has come up empty. Sensitive detectors buried deep underground, shielded from background radiation, have searched for rare collisions between dark matter particles and atoms. Others have looked for annihilation signals in space, where dark matter particles might destroy each other and release radiation. None of these efforts have yielded a definitive signal. The mystery deepens, but the gravitational evidence remains overwhelming. This makes the Milky Way not just a home, but a puzzle. We live inside a structure where most of the mass is invisible. The stars, gas, and dust are only the tip of the iceberg. The halo of dark matter is the hidden bulk, unseen but fundamental. That realization changes our perspective. When we ask how far the galaxy reaches, the answer depends heavily on how we define the edge of the dark matter halo. If we include it, the Milky Way's reach is far greater than the visible disk, perhaps 5 or 10 times larger in radius. The presence of dark matter also shapes the galaxy's future. Our eventual collision with Andromeda will not just be a meeting of stars and gas, but also of dark matter halos. Long before the disks collide, the halos are already interacting. Their overlap may be influencing the motions of both galaxies even now. This invisible component sets the stage for the grand merger billions of years from now, guiding the choreography of cosmic evolution. On smaller scales, dark matter affects the stability of dwarf galaxies orbiting the Milky Way. Some of these dwarfs appear to be dominated by dark matter, with very little visible mass. They're fragile, easily torn apart by tidal forces, yet their survival depends on the cushioning presence of their own dark matter halos. Studying these satellites helps refine our picture of the Milky Way's larger halo. Each orbiting dwarf is both a companion and a probe, a test particle in the larger gravitational field. Even globular clusters, though less dominated by dark matter, provide hints. Their orbits trace the shape of the potential well created by the halo. By measuring their motions precisely, astronomers can refine estimates of the Milky Way's total mass. Current estimates suggest a mass of around 1 to 1.5 trillion solar masses, most of it in dark matter. This figure places our galaxy among the larger members of the local group, though still smaller than Andromeda. Dark matter also complicates the idea of edges. Unlike stars, which eventually thin out, dark matter may extend smoothly and indefinitely, its density decreasing gradually with distance. There is no sharp cut-off, only a fading influence. This means that defining the galaxy's edge becomes an exercise in convention. Do we stop at the virial radius, where the average density drops below a certain threshold? Or do we acknowledge that the halo, in principle, extends even farther, blending into the intergalactic medium? The ghostly glow has no boundary. It simply becomes weaker until it's indistinguishable from the background. For the human imagination, dark matter is both unsettling and fascinating. To live in a galaxy where most of the mass is invisible challenges our sense of reality. We're used to trusting our eyes, but here, our eyes reveal only a small fraction of the truth. The rest is inferred, hidden, ghostly. And yet the evidence is solid. Every orbit, every rotation curve, every cluster motion confirms it. The ghostly glow may not shine, but it surrounds us, shaping our lives in ways we cannot escape. Far beyond the spiral arms and the familiar neighbourhoods of the disk, the Milky Way is surrounded by some of its oldest companions. These are the globular clusters, dense swarms of stars bound tightly together by gravity, orbiting the galaxy in wide paths that carry them far above and below the plane. They're unlike the open clusters found in the disk, which are loose groups of young stars that eventually drift apart. Globular clusters are ancient and enduring. Each contains hundreds of thousands, sometimes millions of stars packed into a sphere only a few dozen light-years across. To look at one through a telescope is to see a glittering ball, every point of light a star as old as the galaxy itself. Globular clusters are wanderers in the sense that their orbits take them through the halo, far from the structured arms and orderly rotation of the disk. Instead of circling in the same direction as the Sun, and most of the stars in the disk, many follow tilted or elongated paths, evidence of a different origin. Some may have formed along with the galaxy itself, relics of its earliest epochs. Others may be the remnants of smaller galaxies absorbed into the Milky Way, their clusters captured and left to orbit as independent systems. Together, they form a population that tells the story of how the galaxy grew, piece by piece, through both internal formation and external accretion. From Earth, globular clusters are among the most beautiful sights in the night sky. M13 in Hercules, Omega Centauri in the southern sky, M22 near Sagittarius, all are visible in small telescopes, and each is a sphere of stars so densely packed that in the core they blend into a continuous glow. For ancient stargazers, these objects were faint smudges, barely distinguishable from stars. With modern instruments, their true nature is revealed, and their significance is profound. They are fossils of the early universe, survivors from a time when the first generations of stars were forming. The ages of globular clusters are staggering. Most are between 10 and 13 billion years old, nearly as old as the universe itself. This means they formed soon after the Big Bang, in the earliest epochs of galaxy formation. Their stars are metal poor, containing very little of the heavier elements created in later generations of stars. This makes them excellent laboratories for studying the early chemical evolution of galaxies. By analysing their spectra, astronomers can trace the history of element production and learn how quickly the Milky Way enriched itself with heavy elements like carbon, oxygen, and iron. Globular clusters are also remarkable for their stability. Unlike open clusters, which disperse after a few 100 million years, globular clusters remain bound for billions of years. Their dense cores keep them intact, even as tidal forces from the galaxy stretch and perturb them. Some clusters show evidence of tidal stripping, with streams of stars trailing behind them as they orbit. These streams provide clues about the gravitational field of the Milky Way, tracing the invisible shape of the dark matter halo. In this way, globular clusters are not just relics but active probes of the galaxy's structure. The orbits of globular clusters extend far beyond the disk, some reaching distances of more than 100,000 light-years. This makes them vital markers of the galaxy's extent. If you want to know how far the Milky Way reaches, look at where its globular clusters orbit. Their presence demonstrates that the galaxy's gravitational influence extends far into the halo, much farther than the spiral arms suggest. In fact, the outermost clusters may be close to the boundary where the Milky Way's halo begins to blend with intergalactic space. Some globular clusters stand out for their unusual properties. Omega Centauri, for instance, is the largest in the Milky Way, containing millions of stars. It may not be a typical cluster at all, but the remnant core of a dwarf galaxy long since absorbed. Its stars show a wider range of ages and compositions than most clusters, suggesting a more complex history. If this is true, then Omega Centauri is both a globular cluster and a fossil galaxy, a reminder that the Milky Way has grown by consuming its neighbours. Other clusters have similarly complex stories. Some appear to be associated with stellar streams, suggesting they were brought in by dwarf galaxies. Each cluster may carry the memory of its origin, encoded in its stars and orbit. By studying them, astronomers can reconstruct the assembly history of the Milky Way, piecing together the mergers and accretions that built the halo. The clusters are like witnesses to ancient events, still orbiting billions of years later. The density of stars within globular clusters creates environments unlike anything near the Sun. In the core of a cluster, stars are separated by only a fraction of a light-year, far closer than in our neighbourhood, where the nearest star is more than 4 light-years away. This proximity increases the likelihood of stellar interactions, such as close encounters, binary exchanges, and even collisions. These interactions produce exotic objects like blue stragglers, stars that appear younger and hotter than the rest of the cluster. They're thought to form when stars merge or siphon material from companions. Globular clusters are natural laboratories for studying such dynamics. From the perspective of life, clusters pose challenges. The crowded environments may make planetary systems unstable, as close encounters could disrupt orbits. Yet it's also possible that some stable systems exist, and the abundance of stars could mean many opportunities for habitable planets. Whether life could thrive in such dense regions is an open question, but the possibility adds another dimension to the study of globular clusters. For astronomers, clusters are also useful distance indicators. RR Lyrae variable stars are common in globular clusters, and their predictable brightness allows distances to be measured with precision. This makes clusters important stepping stones in the cosmic distance ladder. By calibrating distances to clusters, astronomers refine their maps of the Milky Way and beyond. In this way, clusters not only mark the edges of the galaxy, but also help measure them. The population of globular clusters in the Milky Way numbers around 150, though more may remain undiscovered, hidden by dust near the galactic centre. Other galaxies host even more. Andromeda, for example, has several hundred. The number of clusters a galaxy has is related to its mass and history, providing another way to compare and understand galactic evolution. The Milky Way's clusters are not just isolated curiosities, they're part of a broader pattern across the universe. Thinking about globular clusters reminds us that the galaxy is not uniform. It's a collection of structures layered together, each with its own history. The disk, the bulge, the halo, and the clusters all contribute to the whole. The clusters, with their ancient stars and wide orbits, provide the perspective of deep time, connecting us to the earlier stages of galactic formation. They're wanderers, but also anchors, showing us the galaxy's extent and history. When you think of the Milky Way, you might first picture the stars, the blazing giants, the faint red dwarfs, the dense clusters. But stars are only part of the story. Between them lies an ocean of gas, a medium that is both delicate and immense, shaping the life cycle of the galaxy. This gas isn't visible to our eyes in the same way stars are, yet it fills the spaces between them, drifting in clouds, filaments, and diffuse envelopes. It forms the raw material for new stars, it absorbs and scatters light, and it stretches far beyond the bright spiral arms. To understand how far the galaxy reaches, we need to follow where this gas extends, because in many ways it defines the living edge of the Milky Way. The interstellar medium, as astronomers call it, is mostly hydrogen, with smaller amounts of helium and trace elements. Hydrogen exists in different states depending on conditions. In some regions it's atomic, spread thinly across space. In others it's molecular, gathered in dense clouds cold enough for atoms to bond into H2. These molecular clouds are the birthplaces of stars. They are vast, sometimes hundreds of light years across, and within them, gravity can cause knots of gas to collapse into protostars. Around these nurseries, we often see nebulae glowing, lit by the radiation of newly formed stars. The Orion Nebula is one of the best-known examples, visible to the naked eye as a fuzzy patch in Orion's sword. It's a stellar nursery, a pocket of gas and dust where stars are actively forming. On a larger scale, entire spiral arms of the Milky Way are lined with such regions. These are the places where the galaxy continues to renew itself. The gas clouds drift, collide, and fragment, dissolving over time, but in their brief lifespans they see the next generation of suns. Gas clouds don't stay stable forever. They're shaped by the very stars they create. Radiation from hot young stars ionizes surrounding gas, carving out glowing bubbles called H2 regions. Stellar winds push material outward, dispersing the parent cloud. Supernovae explode within these regions, blasting shockwaves that further disrupt the gas. Over millions of years, the original molecular cloud may dissolve completely, its material recycled into the wider interstellar medium. The cycle then begins again elsewhere, as gas gathers into new clouds. This continual drifting and dissolving is part of what keeps the galaxy alive. In addition to molecular clouds, there are vast reservoirs of neutral hydrogen. These atomic gas regions don't glow in visible light, but they emit radio waves at a wavelength of 21 centimeters. By mapping this emission, astronomers can trace the distribution of gas across the galaxy. This method has revealed the spiral arms, even in regions where dust obscures the stars. It also shows that gas extends beyond the stellar disk, reaching into the outer galaxy where few stars are found. The gas clouds stretch farther than the bright arms suggest, forming a faint extended disk that marks another measure of the Milky Way's reach. There's also ionized gas found in the hot interstellar medium. This gas is heated by supernova explosions to millions of degrees, filling bubbles and cavities carved into the disk. These hot regions are difficult to detect directly, but they emit X-rays and leave imprints on the light of distant quasars. The patchwork of cold molecular clouds, warm atomic gas, and hot ionized bubbles makes the interstellar medium a complex and dynamic environment. It's not empty space, but a turbulent mixture, constantly stirred by stellar activity. The reach of gas isn't limited to the disk. Surrounding the galaxy is the circumgalactic medium, a vast halo of hot, diffuse gas extending hundreds of thousands of light-years. This medium is far less dense than the gas in the disk, but it's enormous in volume. It contains as much or more mass in gas as the disk itself. We can't see it directly, but we detect it by looking at the absorption lines it imprints on the light of distant quasars. These observations reveal that the Milky Way is surrounded by a cocoon of gas, stretching nearly to the limits of the dark matter halo. This circumgalactic medium plays a crucial role in the galaxy's evolution. It's both a reservoir and a sink. Gas flows inward from it, feeding star formation in the disk. At the same time, outflows from supernovae and stellar winds pump material back into it. This cycling of gas between the disk and halo is part of the feedback that regulates star formation. Without it, the galaxy would quickly consume its gas and run out of material for new stars. The circumgalactic medium extends the lifetime of star formation by providing a steady, though diffuse, supply. The drifting and dissolving of gas also tells us about boundaries. Unlike stars, which are discrete and countable, gas is continuous. Its density decreases gradually with distance, making it hard to define where it ends. In the outer disk, the gas becomes patchy and faint, but it still extends farther than the last visible stars. In the halo, the gas thins even more, but it's still there, detectable through subtle absorption features. This means the Milky Way's gaseous extent is far larger than its stellar one. The galaxy doesn't stop where the stars fade. It continues in invisible gas, stretching into the intergalactic medium. The scale of these structures is immense. A giant molecular cloud can contain millions of solar masses of gas. The circumgalactic medium may contain tens of billions. These numbers remind us that the galaxy's mass isn't just in stars or dark matter, but also in gas. The drifting clouds are not small details. They're a major component of the system, shaping its dynamics and evolution. Gas clouds also influence the appearance of the sky. Many of the dark patches we see in the Milky Way band are caused by dense clouds blocking starlight. These dark nebulae, like the Horsehead Nebula in Orion, are visible not because they emit light, but because they obscure it. They're part of the same drifting, dissolving medium that creates stars. Without them, the Milky Way would look brighter, but it would also lack the depth and contrast that make it so striking. From the perspective of life, gas is essential. The atoms in our bodies were forged in stars, but before that, they existed in gas clouds. The carbon, oxygen, nitrogen, and iron we rely on all pass through the cycle of drift, collapse, and dispersal. Every breath we take is a continuation of that process. The drifting clouds aren't just astronomical features, they're part of our own history. For astronomers, mapping the gas is both a technical challenge and a source of discovery. Radio telescopes trace hydrogen, infrared surveys reveal molecular clouds, X-ray observatories detect hot gas, and ultraviolet spectra uncover the circumgalactic medium. By combining these methods, we gain a picture of the Milky Way that goes beyond stars. It becomes clear that the galaxy is a complex ecosystem, with gas flowing in and out, cycling through phases, and extending far beyond what we can see. When we think of the galaxy's structure, We usually imagine stars, gas, dust, and dark matter all held together by gravity. But another component threads quietly through the entire system: magnetic fields. They are invisible, intangible, and far weaker than the magnetic pull of a refrigerator magnet. Yet, on galactic scales, their influence is profound. These fields weave through the interstellar medium, guiding the motion of charged particles, shaping the collapse of gas clouds, and tracing patterns that stretch across thousands of light years. To ask how far the galaxy reaches is also to ask how far these invisible threads extend, because they are part of the fabric of the Milky Way, even if we can't see them with our eyes. Magnetic fields in the galaxy are not like the simple dipole field of Earth, with a north and south pole. Instead, they are tangled, structured, and dynamic, shaped by the motions of gas and the rotation of the disk. Observation suggests that the Milky Way's magnetic field has a large-scale spiral pattern, aligned roughly with the spiral arms, but also smaller-scale filaments and loops created by turbulence. In some regions, the field lines are ordered, while in others they are chaotic, twisted by supernova explosions or stellar winds. This complexity makes them difficult to study, but their effects are everywhere. One of the main ways we detect galactic magnetic fields is through the polarization of light. When light passes through dust grains aligned with magnetic fields, it becomes polarized, meaning its waves vibrate preferentially in one direction. By measuring this polarization, astronomers can map the orientation of magnetic fields across the sky. Radio observations also reveal the presence of fields through a process called Faraday rotation, in which polarized radio waves are twisted as they pass through magnetized plasma. These techniques together show that the Milky Way's magnetic field is widespread, extending throughout the disk and into the halo. Even though the field strength is weak, only a few microgauss compared to Earth's magnetic field of about half a gauss, its influence on the interstellar medium is significant. Gas in the galaxy is not just neutral atoms. Much of it is ionized, meaning electrons and protons are free to move. Charged particles respond to magnetic fields, spiraling around field lines and flowing along them. This means that magnetic fields can guide the motion of gas, resisting collapse in some directions while allowing it in others. Star formation itself is influenced by these fields, as they can slow the contraction of molecular clouds, channel flows of material, and even launch outflows from young stars. On larger scales, magnetic fields help shape the galaxy's cosmic rays. These high-energy particles, accelerated by supernova and other energetic events, stream through the galaxy at nearly the speed of light. Without magnetic fields, they would simply escape into intergalactic space. Instead, the fields scatter and confine them, keeping them circulating within the galaxy for millions of years. This confinement not only affects the energy balance of the interstellar medium, but also determines how cosmic rays reach Earth. Every cosmic ray that strikes our atmosphere has been shaped by the invisible magnetic threads of the Milky Way. The halo too contains magnetic fields. Observations show that the fields extend far above and below the disk, threading through the hot, diffuse gas of the circumgalactic medium. These fields may connect the galaxy to the larger cosmic web, linking our home to intergalactic structures. The extent of these fields is difficult to measure, but evidence suggests they may stretch hundreds of thousands of light years, matching the reach of the dark matter halo. If so, the Milky Way is not only surrounded by stars and gas, but also by vast magnetic structures, invisible yet real. The origin of galactic magnetic fields is still uncertain. One idea is that they began as tiny seed fields in the early universe, amplified over time by the motions of gas. The rotation of the disk and the turbulence of supernovae could have strengthened and organized them, creating the large-scale spiral pattern we see today. This process, called a dynamo, operates on scales much larger than anything on Earth, sustaining the fields over billions of years. Whatever their origin, the fields are now integral to the galaxy's structure, an invisible framework as essential as gravity. For us, magnetic fields remain elusive. We don't see them directly, and their effects are subtle compared to the bright stars or glowing nebulae. Yet they influence everything from the shape of molecular clouds to the spread of cosmic rays. They are the hidden threads, stitching the galaxy together in ways we're only beginning to understand. Their reach reminds us that the galaxy's boundaries are not just defined by matter, but also by forces, stretching into space in patterns too delicate for the eye to catch. The presence of these invisible threads also blurs the concept of edges. If the magnetic fields extend into the halo and beyond, then the Milky Way's influence is not confined to the disk or even to its visible stars. It permeates a volume much larger, interacting with the intergalactic medium, connecting with the fields of neighbouring galaxies. The idea of a separate, isolated system becomes less clear. The galaxy is part of a network, stitched together not only by gravity, but also by magnetism. Thinking about these invisible fields adds another layer to the sense of home. It's one thing to imagine the stars we see, the gas clouds drifting, the halo extending outward. It's another to realise that, all around us, unseen lines of force are guiding particles, shaping gas and structuring space. We live inside this magnetic web without ever noticing it, yet it's as much a part of the galaxy as the spiral arms. The invisible threads give the Milky Way depth, extending its reach beyond what we can measure in light. And as we follow these threads outward, we find that they lead us toward a broader question. Does the galaxy even have a true edge, or do all its components, stars, gas, dust, dark matter, and magnetic fields, fade into gradients that never really stop? When we talk about the size of the Milky Way, we often imagine a number, 100,000 light-years across, or 200, or perhaps even more. Numbers are comforting because they suggest precision, but the reality is less precise and far more complicated. Galaxies, including our own, don't have clear edges. They are not islands with shorelines or houses with walls. Instead, they fade. The density of stars decreases gradually. Gas becomes more diffuse, dark matter thins, magnetic fields weaken, and everything blends into the background of intergalactic space. What we call a boundary is really a convention, a definition chosen to make sense of something that doesn't lend itself to sharp limits. In the disk, it's easy to imagine an edge. The spiral arms don't continue forever. They have a finite extent beyond which stars become sparse. Observations suggest that the stellar disk of the Milky Way extends to about 100,000 light-years in diameter, maybe more. But even here, the transition isn't sudden. The density of stars decreases, but there are still stars beyond the disk scattered in the halo. You can't point to a single star and say, "Here is the last one," beyond which none exist. The distribution just becomes thinner, the gradient shallower, until eventually the stars are too rare to count as part of the main body. The same applies to gas. The cold molecular clouds that fuel star formation are mostly confined to the inner disk, within a few tens of thousands of light-years from the centre. Beyond that, atomic hydrogen continues, extending well past the stellar disk. Further still, hot ionized gas fills the circumgalactic medium, stretching hundreds of thousands of light-years. If you define the galaxy by where its gas extends, the size is far larger than if you define it by stars alone. Again, the boundary is a gradient, not a line. Dark matter complicates things even further. Its halo is vast, perhaps 1 million light-years across, overlapping with the halos of neighbouring galaxies. If you define the Milky Way by the extent of its dark matter, then it becomes nearly impossible to say where it ends. Its influence blends into that of Andromeda, long before the visible disks will collide. The boundary is not a separation but an overlap, a merging of influence. This challenges our very notion of what it means for one galaxy to be distinct from another. Even within the galaxy, boundaries are fuzzy. Where does the bulge end and the disk begin? The density decreases gradually, the stellar populations overlap, and the structures interpenetrate. Where does the disk give way to the halo? Again, there's no sharp line, only a change in density and dynamics. The galaxy is a system of layers, but the layers are not stacked neatly. They blend and overlap, each fading into the next. For astronomers, this lack of clear boundaries creates practical problems. When building models, you have to decide where to stop counting. Do you include stars at 120,000 light-years? At 200,000? Do you count all the gas in the circumgalactic medium? Do you include tidal streams from dwarf galaxies, which are technically bound but not part of the original disk? The answers vary, and so estimates of the Milky Way's size vary too. The numbers we see in textbooks, 100,000 light-years, 150,000, 200,000, are not wrong, but they're also not final. They depend on definitions. This idea of gradients rather than boundaries is not unique to the Milky Way. Other galaxies show the same pattern. When we look at Andromeda, we see a bright disk and bulge, but deep observations reveal faint halos of stars stretching far beyond, containing streams from past mergers and diffuse light. Elliptical galaxies, too, fade gradually into the background, with no clear edge. The universe doesn't seem to like sharp lines. Instead, it prefers gradual transitions, shades of density that blur one system into the next. From a human perspective, this is both frustrating and liberating. Frustrating because we want clear answers. How big is the Milky Way? Where does it end? Liberating because it reminds us that nature doesn't conform to our need for neat boundaries. It's messier, more continuous, more nuanced. The galaxy isn't a closed box. It's an open system, exchanging matter and energy with its surroundings, blending into the cosmic web. This openness also changes how we think about home. If the galaxy doesn't have a clear edge, then our home doesn't either. It extends gradually, fading into intergalactic space, connected to the broader universe. To belong to the Milky Way is to belong to something without hard borders, something that reaches out indefinitely. The sense of belonging becomes less about being inside a defined perimeter and more about being part of a gradient, a continuum of matter and influence. Practically speaking, astronomers sometimes define boundaries based on gravitational dominance. The virial radius, for example, is the distance within which the galaxy's gravity is strong enough to hold matter against the expansion of the universe. For the Milky Way, this is around 250,000 to 300,000 light-years. Beyond that, the pull of the galaxy fades compared to the general expansion of space. This is a useful convention, but it's still not a wall. Matter doesn't suddenly stop being influenced by the Milky Way at that radius. The gradient continues, weaker but still present. The blurred edges of the galaxy also highlight its interactions with neighbours. The Magellanic Clouds, for example, are dwarf galaxies orbiting the Milky Way. They are separate systems, yet connected by streams of gas, pulled out by gravitational tides. These streams, known as the Magellanic Stream and Leading Arm, stretch across the sky, linking the dwarfs to the Milky Way. Are they inside our galaxy or outside? The answer depends on how you define the boundary. They're companions, yet also part of the system, their material mixing with ours. The gradient of the galaxy includes them. The same applies to tidal streams from past mergers. The Sagittarius dwarf galaxy is being torn apart, its stars stretched into long arcs around the Milky Way. These streams are technically part of the halo, but they originated elsewhere. Are they the edge of our galaxy or the remnant of another? Again, the boundary is blurred. The galaxy grows by accretion, and its edges are defined not by sharp lines, but by ongoing interactions. For scientists, the idea of gradients is both a challenge and an opportunity. It forces us to think differently about structure. Instead of asking, where does the galaxy end, we ask, how does it fade? How do density, composition, and influence change with distance? The answers provide insight into how galaxies form and evolve. The gradients are the record of that history, written in the distribution of stars, gas, and dark matter. For us, lying under the night sky, the gradients are invisible. We see the bright band of the Milky Way and think of it as a fixed structure, but in reality that band is just the densest part of a system that extends much farther, blending smoothly into the cosmic background. The edges of our home are not edges at all, but gentle transitions, reminders that the universe prefers continuity over separation. Our galaxy does not live in isolation. Although the Milky Way dominates its immediate surroundings with hundreds of billions of stars and a vast halo of dark matter, it is part of a small collection of galaxies known as the local group. This community of galaxies is modest compared to the giant clusters we see elsewhere in the universe, but for us it is everything. Within it, the Milky Way has neighbours both large and small, companions that orbit around it, companions that tug on it, and companions that will eventually merge with it. To understand how far the Milky Way reaches, we have to consider these neighbours, because their interactions stretch and shape our galaxy's edges. The most obvious companions are the large and small Magellanic Clouds, two dwarf galaxies visible from the southern hemisphere as faint smudges of light. They are irregular in shape, full of gas and young stars, and close enough that they can be seen with the naked eye. They orbit the Milky Way, though their paths are complex, shaped by both their mutual gravity and the pull of our galaxy's massive halo. Streams of gas connect them to the Milky Way, torn out by tidal forces, forming the Magellanic Stream that stretches across a significant portion of the sky. These features remind us that neighbours are not separate, tidy systems. They interact, exchange material, and blur the boundaries between them. Beyond the Magellanic Clouds, dozens of smaller dwarf galaxies orbit the Milky Way. Some are faint spheroidals, barely visible against the background of stars. Others are more structured, with their own populations of stars and gas. Many of these dwarfs are satellites, gravitationally bound to the Milky Way, slowly circling it in wide, elongated orbits. Their presence demonstrates the reach of the Milky Way's influence. Our galaxy is not just a disk of stars, but the centre of a complex system of companions, extending its gravitational hold hundreds of thousands of light-years outward. These dwarfs are not permanent fixtures. Some are in the process of being torn apart. The Sagittarius dwarf galaxy is one of the most dramatic examples. Discovered in the 1990s, it is currently being shredded by the Milky Way's gravity, its stars pulled into long tidal streams that wrap around the sky. These streams weave through the halo, evidence that the Milky Way grows by cannibalizing its neighbours. Each small galaxy that drifts too close becomes part of our own, its stars scattered into the halo, its gas feeding new star formation. The edges of the Milky Way are defined as much by these encounters as by its own internal structure. The process is not one way. While the Milky Way consumes smaller neighbours, it is also influenced by them. The gravitational pull of the Magellanic Clouds, for example, may warp the disk of the Milky Way, creating ripples in its structure. Observations suggest that the outer disk is not perfectly flat but bent, a possible result of these interactions. The streams of gas flowing in from the clouds may also fuel star formation in the Milky Way, providing a fresh supply of material. Our neighbours are not just passive victims, they actively shape the evolution of the galaxy. The local group also contains another giant, the Andromeda galaxy. Larger than the Milky Way, with perhaps twice as many stars, Andromeda is currently about 2.5 million light-years away, but it is moving toward us. In about 4 billion years, the two galaxies will collide. This future merger is one of the defining events of our galaxy's destiny. Long before the disks overlap, the halos of dark matter and gas already interact, their edges blending. In that sense, the meeting has already begun. The Milky Way's reach is not confined to its own stars, but extends into the shared space where it and Andromeda are slowly converging. Other members of the local group also interact with us. The Triangulum galaxy, smaller than Andromeda and the Milky Way but still substantial, is likely bound to Andromeda and may play a role in the eventual merger. The faintest dwarfs, like those discovered in recent surveys, orbit on the fringes of the Milky Way's halo, barely distinguishable from isolated star clusters. Each of these neighbours is part of the broader system, part of the network that defines our galaxy's environment. For astronomers, these interactions are not just curiosities, they are laboratories for studying how galaxies evolve. By mapping the tidal streams, gas flows and orbital motions of our neighbours, we learn about the distribution of dark matter, the mass of the Milky Way, and the processes that build galaxies. The neighbours are test particles in a grand experiment, their motions tracing the invisible structure of the halo. Without them, we would know far less about our own galaxy's extent. On a deeper level, these encounters remind us that galaxies are not static. They are dynamic systems, constantly shaped by gravity, mergers, and flows of matter. The Milky Way we see today is the product of countless past interactions, and the one we see in the future will be different again. Our neighbours are part of that story. They are not just companions, they are building blocks. Each one that merges becomes part of the Milky Way, extending its reach and enriching its history. For those of us lying under the night sky, the presence of neighbours is easy to forget. The stars we see belong mostly to our own disk. The Magellanic Clouds are visible only from certain latitudes, and the dwarfs are invisible without telescopes. Andromeda is a faint smudge, easily overlooked. Yet these faint companions are part of our story, just as much as the bright band of the Milky Way. They remind us that our galaxy is not alone, that it lives in a community, and that its reach extends outward through interactions as much as through its own structures. Among all the Milky Way's neighbours, two stand out not only for their proximity, but also for their brightness. The large and small Magellanic Clouds are visible to the naked eye from the southern hemisphere, appearing as hazy patches of light hanging in the night sky. For people who live under those skies, they have been familiar for as long as anyone has looked upward. Long before telescopes, these companions were noticed, named, and woven into stories. Today, astronomers know them as dwarf galaxies orbiting the Milky Way, irregular in shape, rich in gas, and deeply entangled with our galaxy's history and future. The Large Magellanic Cloud, or LMC, is the bigger of the two, lying about 160,000 light-years from us. It contains tens of billions of stars, making it one of the largest dwarf galaxies known. The Small Magellanic Cloud, or SMC, is smaller, with a few billion stars, and lies about 200,000 light-years away. Together they are among the closest galaxies beyond the Milky Way, and because of that proximity, they have been studied in detail across the electromagnetic spectrum. Their orbits and interactions with each other and with the Milky Way have created streams of gas and distorted shapes, evidence of ongoing gravitational tug-of-war. The Magellanic Clouds are not simple companions. They are bound to each other, orbiting in a pair, and together they orbit the Milky Way in a complex dance. Their mutual gravity, combined with the pull of the Milky Way's massive halo, creates tidal forces that strip gas and stars from them. This stripped material forms features like the Magellanic Stream, a long ribbon of hydrogen gas stretching across more than 100 degrees of the sky. The stream is invisible to the eye but detectable in radio waves, and it shows just how deeply the clouds are connected to the Milky Way. The Large Magellanic Cloud is home to some remarkable features. One of the most famous is the Tarantula Nebula, the most active star-forming region in the local group. It is a giant complex of gas and young stars, many times more energetic than the Orion Nebula in our own galaxy. If the Tarantula Nebula were as close as Orion, it would cast shadows on Earth. The presence of such a massive nursery in the LMC shows that dwarf galaxies, though smaller than spirals, can still be powerhouses of star formation. The stars born there will shine for millions of years, and some will explode as supernovae, enriching the galaxy and contributing to the flow of elements into space. The Small Magellanic Cloud is less massive, but it too contains active star-forming regions and clusters. Its structure has been distorted by tidal interactions, giving it an irregular shape. Bridges of gas connect it to the LMC, evidence of their ongoing exchange. Together, the clouds are not static satellites but dynamic systems, constantly reshaped by gravity and by their interactions with the Milky Way. Their irregular forms are records of those interactions, scars of tidal forces that continue to act today. For astronomers, the Magellanic Clouds are important laboratories. Their proximity allows us to study star formation, stellar evolution, and galactic dynamics in detail. They're close enough that individual stars can be resolved, yet far enough to provide a view of entire systems. By examining them, we learn not only about dwarf galaxies, but also about how larger galaxies like the Milky Way grow and evolve. The clouds are reminders that galaxies do not exist alone. They exist in groups, exchanging matter and influencing one another. Their role in shaping the Milky Way is significant. The Magellanic Stream, for instance, may eventually feed star formation in our galaxy. As the gas drifts inward, it could replenish the interstellar medium, extending the Milky Way's ability to create new stars. At the same time, the gravitational pull of the LMC may be warping the Milky Way's disk, creating ripples that astronomers have observed in the outer regions. These effects demonstrate that even small companions can have large impacts, especially when they are as massive as the LMC. The future of the Magellanic Clouds is likely to be absorption. Over billions of years, they will spiral inward, pulled by dynamical friction as they move through the Milky Way's dark matter halo. Eventually, their stars and gas will become part of the Milky Way, their individuality lost but their material preserved. This process has happened many times before with other dwarfs. The difference is that the clouds are bright and close enough for us to watch the process unfold. They are living examples of how galaxies grow, through the steady accretion of smaller systems. From a human perspective, the Magellanic Clouds are striking reminders of our place in the cosmos. To stand under a southern sky and see them hanging there is to realize that we live in a galaxy with companions visible to the eye. For those in the northern hemisphere, where the clouds are never visible, their absence is a reminder that the view of the universe depends on where you are. The sky is not the same everywhere. In the south, the Magellanic Clouds are part of the natural landscape of the night, just as much as the Milky Way itself. The clouds also blur the definition of the Milky Way's edge. Are they part of the galaxy or separate? They orbit within the halo. Their gas streams connect to the disk. Their future is to merge with us. Yet for now, they remain distinct, their own galaxies with their own structures. The boundary between them and the Milky Way is not sharp, it is a gradient, a region of interaction and exchange. The Milky Way's reach includes them, even if they are technically outside its main body. Studying the Magellanic Clouds also helps refine our understanding of dark matter. The motions of the clouds, their orbits, and their tidal features depend on the distribution of dark matter in the Milky Way's halo. By modelling their interactions, astronomers can test different halo shapes and sizes. The clouds are like test particles on a grand scale, their motions revealing the invisible mass around us. They remind us that our neighbours are not just companions but tools for probing the unseen structure of our galaxy. When smaller galaxies or clusters wander too close to the Milky Way, they don't remain intact forever. Gravity, relentless and patient, pulls on them unevenly. The side closer to the Milky Way feels a stronger tug than the far side, stretching the system out along its orbit. Over time, stars are stripped away, forming elongated trails that wrap around the galaxy. These are the stellar streams, rivers of stars pulled and scattered across the halo. They are faint, often invisible to the naked eye, but with careful observation they can be traced, and they reveal the ongoing growth of the Milky Way. One of the most prominent examples is the Sagittarius Stream. It is the remnant of the Sagittarius dwarf galaxy, which has been orbiting the Milky Way for billions of years. Each pass brings it closer, and each pass strips away more stars. What remains is a core still visible today, but much of its mass has been stretched into long arcs that encircle the Milky Way. These arcs cross the sky in great loops, wrapping around in multiple passes. They are the visible scars of a galaxy being digested. The stars in the stream now orbit the Milky Way, indistinguishable in time from those born here, yet their origin is preserved in their motions and compositions. Other streams are subtler. Some originate from globular clusters disrupted by tidal forces. These streams are narrower, like thin ribbons rather than broad rivers. The Palomar 5 stream is a famous example, traced from a globular cluster that is slowly being torn apart. Its stars stretch outward in both directions, forming a delicate line across the sky. Streams like these demonstrate that even dense clusters, which can survive for billions of years, are not immune to the galaxy's pull. Over time, they too dissolve, their stars added to the halo. Detecting these streams requires precision. They are faint, often spread across huge portions of the sky. Surveys like Gaia, which measures the positions and motions of over 1 billion stars, have revolutionized their study. By mapping how stars move, Gaia can reveal coherent groups traveling together even when they are barely distinguishable from the background. This has led to the discovery of many new streams, each a trace of past accretion. The halo, once thought to be a smooth distribution of stars, is now seen as a tapestry of overlapping streams, each telling the story of a merger. The importance of these streams goes beyond history. They are sensitive probes of the Milky Way's gravitational field. The paths they follow depend on the distribution of mass, including dark matter. If the halo were perfectly smooth, the streams would follow predictable orbits. But if the halo is clumpy, with dark matter substructures, the streams are perturbed, bent, or broken. By studying these distortions, astronomers can test theories of dark matter, looking for evidence of small-scale clumps predicted by simulations. Stellar streams are not just relics. They are tools for exploring the invisible structure of the galaxy. The number of known streams continues to grow. Each new discovery adds detail to the picture of how the Milky Way assembled itself. Some streams trace dwarf galaxies like Sagittarius. Others trace globular clusters. Together, they reveal that the halo is not static but dynamic, constantly shaped by accretion. The stars in these streams are often old and metal-poor, consistent with origins in smaller systems. Their presence confirms that the Milky Way has grown by consuming many companions, not just one or two. The scale of these structures is immense. Some streams stretch tens of thousands of light years, wrapping around large portions of the galaxy. To imagine them is to picture rivers of stars flowing across the halo, looping around the disk, sometimes intersecting each other. They are not visible rivers like the Milky Way band in the sky, but they are there, woven into the background, faint threads in the fabric of the galaxy. For us, living inside the disk, the streams are hard to see directly, but their presence is a reminder that the galaxy is not a closed system. It is porous, constantly interacting with its surroundings. Each stream represents a connection between the Milky Way and another system, a line of evidence that our galaxy grows not in isolation but through encounters. The edges of the Milky Way are not quiet. They are busy, filled with these remnants of past interactions. The fate of stars and streams is to become part of the halo. Over time, their orbits will mix, and the streams will dissolve into the general population. The memory of their origin will fade, except in subtle signatures preserved in chemical composition. But while they last, they are clear markers of the galaxy's growth. They are living fossils, visible for a time before blending into the whole. Thinking about streams also changes how we view the question of edges. If the Milky Way is surrounded by stars that once belonged to other galaxies, where do we draw the line between ours and theirs? Once the stars are stripped, they orbit the Milky Way, becoming part of it. The streams blur the boundary between inside and outside, just as gas flows and dark matter halos do. They remind us that galaxies are not fixed entities but processes, constantly changing, constantly absorbing. The streams also connect to the future. As the Milky Way continues to interact with its neighbours, more streams will form. The Magellanic Clouds, for instance, already show signs of tidal stripping. In time, Their stars too will stretch into arcs, weaving new rivers around the galaxy. The future Milky Way will be surrounded by even more streams, evidence of ongoing growth. And when the galaxy eventually merges with Andromeda, the combined system will be filled with even grander streams, remnants of that colossal collision. For astronomers, the beauty of streams lies in their dual role as history and experiment. They are traces of ancient encounters, fossils of the galaxy's past. But they are also sensitive tests of physics, revealing the distribution of dark matter, the shape of the halo, and the processes of galactic evolution. Each stream discovered is another thread in the tapestry, another clue to the puzzle of how galaxies form and grow. For us they are invisible, yet their existence expands our sense of home. The stars above are not all native to the Milky Way. Some were once part of other galaxies, now woven into ours. Our home is larger and more inclusive than we might think. It is not just the disk and the bulge, it is the sum of all the stars bound by gravity, whether born here or captured. The streams of stars pulled and scattered remind us that home is not about origin, but about where gravity brings you. And as we hold that thought, the question naturally arises, if the Milky Way grows through these streams, and if its edges are defined by constant interactions, does it even make sense to talk about an edge at all? Or should we think of the galaxy as something with no true boundary, only a gradual fading into the wider universe? When we imagine the Milky Way, it's natural to picture it as something with an outline, a border, a place where it stops. That's how we think about most things. A city has limits, an ocean has shores, a forest gives way to plains. But a galaxy isn't built that way. Instead of clear lines, it has layers and gradients. The stars thin, the gas becomes diffuse, the dark matter fades, the magnetic fields weaken. At no point is there a wall, a hard edge that separates the Milky Way from what lies beyond. Asking whether the Milky Way has an edge is like asking where the air around Earth ends. You can go higher and higher, and at each step there's still some air, thinner and thinner, until eventually you're in space. But no sharp surface divides the two. If you define the galaxy by its bright disk of stars, then you might say it has a size of about 100,000 light-years across. That number appears in books and lectures, and it's not wrong. The spiral arms don't extend indefinitely. They peter out after tens of thousands of light-years, leaving fewer stars and less structure beyond. For many purposes, that's a useful definition. But it's only one layer. Surrounding the disk is the halo, populated by old stars, clusters and streams. This halo stretches much farther, perhaps 200,000 light-years or more. If you use the halo as your boundary, the galaxy is far larger than the disk suggests. Then there's the dark matter halo, inferred from the motions of stars and gas. This halo may extend hundreds of thousands of light-years, perhaps as far as 1 million. Its gravitational influence overlaps with that of Andromeda, our nearest large neighbour. If you take dark matter into account, the edge of the Milky Way is not distinct from the edge of Andromeda. The two halos blend together long before the disks will collide. By this measure, our galaxy has no isolated edge at all. It is already merging in a sense with its neighbour, part of a continuous fabric of gravity that ties galaxies together. The question of edges becomes even more complicated when we consider gas. The interstellar medium extends beyond the visible disk, and beyond that lies the circumgalactic medium, a vast envelope of hot, diffuse gas surrounding the Milky Way. This gas stretches hundreds of thousands of light-years, maybe farther, and may contain as much mass as the disk itself. We can't see it directly, but its presence is revealed by how it absorbs light from distant quasars. If this gas is part of the Milky Way, then our galaxy reaches far beyond the limits of the stars. So does the Milky Way have an edge? The answer depends on what you mean by edge. If you mean the visible boundary of the disk, then yes, there's an approximate size. If you mean the full extent of stars and clusters, then the edge is farther out, but still fuzzy. If you mean the reach of gas, magnetic fields and dark matter, then there is no clear edge at all, only a gradual blending into the intergalactic medium. The concept of an edge is more about our need for definitions than about the reality of the galaxy. For astronomers, this fuzziness is both a challenge and a source of insight. It forces us to think of galaxies not as islands, but as parts of a continuum. The Milky Way is not separate from its surroundings. It exchanges material with the intergalactic medium, pulls in dwarf galaxies, sends out streams, and overlaps with its neighbours. It is less a neatly bounded object than a node in a cosmic web, connected by filaments of dark matter and gas. From a human perspective, the idea that the galaxy has no edge is unsettling and fascinating at the same time. We're used to thinking of a home as something bounded, but our galactic home doesn't stop anywhere in particular, it just fades. That fading is a reminder that nature doesn't care about our categories. It operates by continuity, by gradients, by processes that stretch across space and time. This lack of a sharp edge also reminds us of the galaxy's history. The Milky Way has grown by merging with smaller galaxies, and each merger blurs the boundary further. The stars of the Sagittarius dwarf galaxy, now stretched into streams, are technically part of the Milky Way. But when did they become part? When the first stars were stripped? When half the galaxy was absorbed? Or only once the remnant disappears? The question has no clear answer, because there was no single moment when the boundary was crossed. Growth is gradual, and so are edges. The same will be true in the future. As the Magellanic Clouds spiral inward, their stars will eventually become part of the Milky Way. As Andromeda approaches, its halo already overlaps with ours. At what point will the Milky Way stop being itself and become part of a new, merged galaxy? Again, there is no sharp transition. It will fade from one identity into another. The concept of edges is a human convenience, not a cosmic fact. Thinking about edges this way changes how we understand scale. When we say the Milky Way is 100,000 light-years across, we're giving one definition. But when we include halos, streams, gas, and dark matter, it might be 1,000,000. The difference is huge, but both numbers are true in their own way. They reflect different layers of the galaxy, different definitions of what it means to belong. The Milky Way is not a single size, it is many sizes depending on what you count. For those lying under the night sky, this ambiguity is invisible. The band of the Milky Way looks like a clear structure, a ribbon of stars cutting across the darkness. It feels bounded, like something you could outline. But what you're seeing is only the densest part, only a slice of the whole. The edges of that band are not edges of the galaxy. They're just where the density drops enough that your eyes can't detect more. Beyond them, the galaxy continues, in faint stars, in gas, in dark matter. The edge is not out there in space. It is in your perception. Astronomers sometimes define the edge in terms of influence, where the Milky Way's gravity dominates. By that measure, the galaxy extends until its pull is balanced by the expansion of the universe or by the gravity of other galaxies. But even this is a gradient, not a sharp line. Influence fades with distance but never quite vanishes. Every star, every particle of dark matter, every cloud of gas has some gravitational effect, however small, extending infinitely. The galaxy, in that sense, has no edge at all, and so the question is less about where the Milky Way ends and more about how it connects. It connects to its neighbours through overlapping halos, it connects to the intergalactic medium through gas flows, it connects to the cosmic web through filaments of dark matter. The galaxy doesn't stop, it blends. Our home is not an isolated object, but a node in a network, one point in a universe where everything is linked. If there is no clear boundary, then what happens when the Milky Way merges with Andromeda? How do two galaxies without edges become one? The Milky Way may seem vast and eternal, but like all things in the universe, it is not static. It has a future shaped by gravity, and one of the defining events in that future will be its collision with the Andromeda galaxy. Right now, Andromeda lies about 2.5 million light-years away, visible to the naked eye as a faint smudge in the constellation Andromeda. It is the most distant object you can see without a telescope, and yet in cosmic terms, it is close. Measurements show that Andromeda is moving toward us at about 110 kilometers per second. Slowly but inevitably, the two largest galaxies in the local group are on a collision course. The word collision can be misleading. Galaxies are made mostly of empty space, with stars separated by vast distances. When the Milky Way and Andromeda meet, the stars themselves will almost never hit one another. Instead, the collision will be gravitational, with the two galaxies passing through each other, distorting each other's shapes, and eventually merging into a single, larger system. The process will take billions of years, unfolding slowly compared to human timescales. But for the galaxy, it will be transformative, reshaping its structure and redefining its reach. The first close pass will occur in about 4 billion years. As Andromeda approaches, its disk will fill more and more of our sky, eventually appearing larger than the Milky Way does now. At that distance, tidal forces will begin to stretch both galaxies, pulling out long tails of stars and gas. These tidal features are seen in other galaxies that are colliding today, captured in telescopic images of the universe. In our case, the Milky Way and Andromeda will form enormous arcs and streams, wrapping around each other in graceful but chaotic patterns. After the first pass, the galaxies will swing apart, but gravity will pull them back together. Over the next few billion years, they will oscillate, colliding again and again, each time losing energy to tidal interactions and dynamical friction. With each pass, they will come closer until eventually their cores merge. By then, the spiral structures will be destroyed, replaced by a more amorphous shape. Simulations suggest the result will resemble a giant elliptical galaxy, sometimes called Milkomeda. The exact outcome depends on details of the collision, but the transformation will be profound. The fate of our Sun in this event is uncertain. It lies far from the galactic center, in one of the spiral arms. During the merger, its orbit may be disturbed, flung outward into the halo or inward toward the center. Simulations show that many stars will be scattered to new positions, but direct collisions will remain rare. To an observer on Earth, if any descendants of life are still here, the sky will change dramatically. Instead of the familiar band of the Milky Way, there will be arcs of stars, bright tails, and eventually the swelling core of a merged galaxy dominating the heavens. The night sky will become a spectacle unlike anything we see today. The merger will not be destructive in the sense of stars colliding, but it will trigger new waves of star formation. As gas clouds are compressed during the collision, they will collapse into new stars. Starbursts will light up regions of the merging galaxies, creating clusters and nebulae. Over time, much of the gas will be used up or expelled, leaving the merged system with less fuel for star formation. That is why giant elliptical galaxies, often formed by mergers, contain older stars and less gas. The Milky Way and Andromeda, once spirals rich with gas, will eventually become a more quiescent system, glowing with billions of long-lived stars but forming few new ones. This future collision is not unusual. Galaxies collide and merge throughout the universe. In fact, this is the main way galaxies grow. The Milky Way itself has already merged with many smaller galaxies, as the stellar streams in its halo show. The difference with Andromeda is scale. This will be the first time the Milky Way merges with another giant, an event on a much grander level than the absorption of dwarfs. It is a natural step in the life cycle of galaxies, part of the ongoing evolution of cosmic structures. From a broader perspective, the merger will also affect the local group as a whole. The Triangulum galaxy, the third largest member, may join the collision, either before or after the main merger. The outcome will be a single massive galaxy at the center of the local group, surrounded by remnants of smaller dwarfs. Over even longer timescales, billions of years beyond the merger, this new galaxy will drift together with others in the local group, as cosmic expansion isolates galaxy clusters from one another. The local group itself may collapse into a single giant elliptical, the last island of stars visible in our corner of the universe. Thinking about this future brings us back to the question of edges. During the merger, the halos of the Milky Way and Andromeda will overlap completely, blending into a single halo. The distinction between the two galaxies will fade long before their disks merge. In that sense, the collision has already begun. Their dark matter halos are already touching, their circumgalactic media already mixing. The great future collision is not a sudden event but a gradual process, one that began long ago and will continue long after the disks merge. For us, the collision lies far in the future, long after the Sun has left its main sequence and Earth as we know it has changed. But in cosmic time, 4 billion years is not so long. The Milky Way itself is more than 10 billion years old. The merger with Andromeda is simply the next chapter in its story, the next step in a sequence of growth and transformation that has been unfolding since the beginning. The galaxy is not fixed. It is a process, always changing, always interacting. The Great Collision is just another phase of that process. From the perspective of life on Earth, the merger may not matter. By then, the Sun will be nearing the end of its stable lifetime, swelling into a red giant in another billion years or so. Earth may no longer be habitable, regardless of the cosmic drama unfolding above. But for the galaxy, the merger is momentous. It will reshape its structure, its star formation, its identity. The Milky Way as we know it will cease to exist, replaced by something new, larger, and more diffuse. For astronomers, this future collision is a reminder of the scale of cosmic time. The events we describe are far beyond human lifespans, yet they are as real and certain as the motions of planets. The calculations of orbits, the measurements of velocities, all point to the same conclusion. The Milky Way and Andromeda are bound to meet. It is written in the sky, waiting for its time. And as we sit with that thought of two great galaxies slowly drawing together, it leads naturally to the question of identity. When the Milky Way merges with Andromeda, what will become of the name, the idea, the sense of belonging we attach to our galaxy? What does it mean for our home when it transforms into something else? We've travelled through the spiral arms and the bulge, the dust lanes and the halo, the globular clusters and the Magellanic companions. We've drifted into the invisible realms of gas and magnetic fields, considered the faint rivers of stars scattered by tidal forces, and thought about the reach of dark matter. We've followed the story forward to the future, where the Milky Way merges with Andromeda, changing into something larger and unfamiliar. And now we're left with the question of where our place in all this truly ends. It's easy to think of the galaxy as a thing, a single entity with a defined size, a boundary and a history. But the deeper we look, the less it seems like an object, and the more it seems like a process. Stars are born and die. Gas collapses, forms planets, and then drifts outward again. Smaller galaxies fall in and are absorbed. Dark matter halos blend with neighbours. Every part of the Milky Way is in motion. Every part is temporary. The edges are not sharp because nothing here is permanent. The galaxy is more like a current than a container, a flow that continues on timescales longer than we can imagine. When we try to ask where our place truly ends, we discover that there isn't one simple answer. If we think about the disk, then our place ends a little beyond the spiral arms, perhaps 100,000 light years away. If we think about the halo, then our place stretches twice or 3 times as far, fading into a scattering of old stars. If we think about dark matter, then our place extends hundreds of thousands of light years, maybe close to 1 million, already overlapping with Andromeda. If we think about gas, the circumgalactic medium stretches almost as far, linking us to the cosmic web. At each scale, the answer changes. Our place is small and large at the same time, depending on what we count. And maybe that's the real lesson. Our home is not a simple shape with a clear outline. It's a set of connections between stars, between systems, between galaxies, between the universe itself and the matter inside it. The Milky Way is one of countless galaxies, but it is the one that holds our sun, our earth, our lives. Its lack of an edge does not make it less of a home. It makes it richer, more continuous, part of something larger. Where our place ends is not at a line, but at a transition into the next thing, the next structure, the next connection. For human beings, living on a small planet in the outskirts of one spiral arm, these scales are beyond comprehension. Yet they matter to us because they shape the conditions that allowed us to exist. Without the gas clouds, there would be no stars. Without the cycles of collapse and dispersal, there would be no heavy elements. Without the dark matter halo, the galaxy would not hold together long enough for life to form. Without neighbours, the Milky Way would not have grown into the system we know. Every part of its reach has contributed to our existence, even the parts invisible to our eyes. So where does our place end? On one level, it ends where gravity weakens into the pull of other galaxies, where the halo blends with Andromeda's, where the local group itself becomes the defining unit. On another level, it doesn't end at all. The particles of gas escaping into intergalactic space are still part of our story. The streams of stars pulled from other galaxies and added to ours blur the distinction between us and them. The universe itself is a continuum, and we are part of that continuum. The Milky Way is one scale of belonging, not the only one. For astronomers, defining the edge is a practical matter, needed for calculations and models. For us lying under the stars, it's a philosophical matter. It asks what we mean by home. Is home the spiral arms, the halo, the local group, the universe? Each answer is true in its own way. Each expands our sense of place, showing us that we belong not just to Earth, not just to the Sun, but to an unfolding structure that extends across space and time. When we think of it this way, the closing reflections are not really an ending. They are a continuation. The galaxy doesn't stop, it just blends into the next thing. Our place doesn't end, it just expands into broader scales. To belong to the Milky Way is to belong to something without a final edge, something that continues into the universe itself. And as you let that thought settle, you can return to the night sky, to the quiet band of the Milky Way stretched above. What you see is only the surface, only the part bright enough to touch your eyes. Behind it are halos, streams and unseen mass. Beyond it are neighbours, mergers, and futures still to come. There is no final line, no last border. There is only the continuity of connection, the fading of one structure into another, the gradual blending that means our place doesn't truly end at all. Thank you for drifting through this journey tonight. If you found it soothing, or if it helped you unwind, you're welcome to stay connected here, where we take these long, slow explorations of science together. You can always return when you need a calm voice and a vast horizon to think about. For now, let yourself rest with the thought that you're part of something immense, still unfolding, without edges. The stars will be here whenever you look up again, and so will this quiet space. Sleep well.